All right, everyone. So thank you for tuning in to this webinar. Thank you, Rob, for putting it together. I hope everyone's staying safe and healthy. Per Rob, what we're going to do is we're going to have the comments being watched throughout this entire webinar. So if you have any thoughts, ideas, questions, concerns, that kind of thing, while any of these four companies, AirTurbine, Harvey, Fifth Axis, and Autodesk are presenting, just type it into the comment section. And what we're going to do is we're going to answer at the end of each individual presentation any of the questions that are pertinent to what's going on. Some of you might know that this is something that the four companies, we had started this and we were traveling around the country doing this road show, and it started to really gain some momentum. And the entire purpose was, in order to generate success, we wanted to educate, well, anyone who was interested, but hopefully the world in general, in high-speed machining, micro machining, manufacturing. And in order to do that, we all realize that there's a significant symbiotic relationship between what each of us are doing, that we must connect with one another in order to create overall success for all the customers and all the machine companies and everyone in general. Because if I sell an AirTurbine tool and you don't have rigid work holding, or you don't have the right cutters, or you haven't programmed this effectively and correctly, you're going to break the tools. You're not going to get the finish you want. You're going to wonder why that AirTurbine isn't producing the results that I say you can produce, based on some of the other conflicts that might be going on. So we brought everyone together, and we're going to each do the best we can in educating you on our specific technology. And then we'll kind of bounce ideas off of each other as well, because we've been doing this for a little while and it's been fun. So with that, let's go ahead and get started. I'll share my screen. All right. So as I mentioned, we're all going to come together and talk about the significant properties of what our products can do. Through AirTurbine, I'm going to start things off, and I'm kind of going to give an overview on how we can all be successful with high-speed machining. I'm going to talk a little bit about what RPM can do for everyone. I'm going to go over some of the complications of where you might find struggle and how to solve those problems, which I'm sure many of us are going through the difficulties and then would like to find a solution as well. So I want to share with you guys, if this thing goes forward, a good friend of mine. This gentleman's name is Peyton Dean, and apparently my laptop is going slow, so we've skipped ahead for just a moment, so bear with me. And I'll go back to my buddy Peyton. So Peyton is a 19-year-old kid. He has a DM2. He's based out of Seattle, Washington. Just recently, I had the great opportunity to be a part of his podcast, and it was really exciting and educational. But I was out there visiting him, and I noticed that he was running a 15-thou diameter ball mill, and that ball mill was going about 3 inches a minute. And what we were able to do simply by, all we did was change a 10,000 RPM main spindle and change it up to 50,000 RPM. And that cycle time was reduced from 3 hours down to 9 minutes. On top of that, we were able to go from 3 inches a minute to 100 inches a minute just by increasing the cycle time. So the reason I want to start with this is just to show what success can happen by applying the right techniques to an existing operation. There wasn't anything crazy done. It was simply adding RPM to the existing program. These guys here are my friends in India. They're based out of Pune, India. Their company name is called Torque Motors. And Torque Motors makes a really cool electric motorcycle that goes for about 300 or 3,000 US dollars. And we were able to reduce the cycle time on all of their components by 50% or more, from electrodes in copper to slotting in aluminum to engraving in steel. We were able to reduce each one 50, 60, 75% or more their cycle times. Again, this is all we did was change from 5,000, 8,000, 10,000 RPM on up to 50 and 65,000 RPM. So what is high-speed machining really? And this often gets complicated in the sense of people go, well, it's when I can move my machine really, really fast, which is true. And other people say, well, it's when I can spin my tool at, 100,000 RPM, which is also kind of true. But what we're trying to create is a perfect relationship between that feed rate, that depth of cut, that RPM, and that rigidity of the work holding. And so what we're doing is we're taking light cuts and flying through it as quick as you can do. Now, a lot of people in their mind, or they have a certain mindset that says, okay, well, I'm going right now with my 1/8 inch tool, I'm going an 1/8 inch deep. And if I'm going to change my RPM from 10,000 RPM up to 50,000 RPM, I can keep my same depth of cut at an 1/8 inch deep, but I can go 5 times faster in my feed rate based on going 5 times faster in my RPM. And that's not actually how high-speed machining and micro machining work, based on the tool rigidity as well. And that's why we want to define what is high-speed machining and the ability to do light, very fast passes to create that same material removal rate that was that we want to get. So what are some of the challenges? Obviously, this kid doesn't have much of a challenge doing that. I wish I could do that. But so what are some of the challenges? Now, I think a lot of these challenges are obvious in the sense that they're easy to find out. It's really easy to figure out when I'm making a mistake, because either I'm losing tool life that I shouldn't be losing, or my finish isn't what I want it to be, or I'm breaking my tools, or my cycle time just isn't as reduced as I thought it would be. So what are some of the challenges? And the first challenge is metals can get extremely hard when heated. So this can cause tool failure, vibration and chatter. So we're going to get way more into vibration and chatter a little bit later, but vibration and run out will be two of the most important things that you need to concern yourself with in order to have success. Vibration being rigidity, and chatter also can be in there, and run out can also be with chatter, but vibration and run out are going to be very important. Small diameter tools, the smaller you get in your tool diameter, the deflection of that tool becomes less rigid. And so what happens when you become less rigid is you must spin faster. We have to have a higher RPM in order to create the cutting force velocity that's needed when we're spinning in a circle to create that force needed to go through material. So RPM is very important. And then tool pass. Different tool pass, as you guys probably know, working in different parts of the world and different materials and all that kind of fun stuff. You're going to want to create a tool path that benefits you when you're going at the higher RPM and doing lighter cuts and faster feeds. Otherwise, your cycle time isn't going to be as reduced as you think it could be. But if you utilize your software effectively, which Jack is going to talk about with Fusion 360, you're going to see some major differences in the capability of what you can accomplish. Micro end mills live in a different world than most cutters are used to. My friend Don is going to go over a lot of this with Harvey Tool. He knows far more than I do. I think a lot of what happens is I know how to break them, and he knows how to tell me how to not to break them. But the feeds and speed formulas and calculations that work for larger cutters typically don't work in the same world when you get into micro machining. Harvey Tool, to my knowledge, has a nice mathematical calculation that Don is gonna share with you to maybe get a good starting point of where we could be in calculating depth of cut, feed rate, the amount of rigidity a tool can have. But we suggest that the cutting physics start to set with tool diameters at 1/8 inch and below. And with small cutters, the cutting force is twice what conventional calculations suggest, which compounds the problem of that rigidity and tool deflection based on how thin it is. So if it's gaining more force than a larger tool, and it creates more deflection and it's less rigid, that obviously makes these tools more delicate, in which case we must have higher RPM. So rigidity, vibration, this is the #1 issue in high-speed machining, the #1 enemy. And it's not just how rigid my product is at AirTurbine or how rigid the product at Fifth Axis is with holding the material. It is from the machine spindle all the way down to the rigidity of the machine table. And I'm sure you guys are reading it right now, but any one of these pieces, from the machine spindle to the tool holder to the extensions to the workpiece to the machine table, any one of those aren't as rigid as they should be. And that'll be the weakest point, which would be the start of bringing down the ultimate success that you want to have while high-speed machining. So how big is a micron, and what is the importance of runout? As you can see to the right-hand side, it's the right-hand side for me. I think it's the right-hand side for you guys as well. A human hair is massive compared to a micron, and I think a lot of you guys know that already. A micron is just, it's tiny, and the ability to create runout at such precision not only is important, but it's something that not everyone can do. And when the smaller you get in tool diameter, the more rigid things need to become, the more important that runout is. But what happens when you don't have good runout? What happens when a tool is not perfect, or a spindle isn't spinning as symmetrical as you'd like? What happens is it causes more flutes to cut deeper than another flute, which is going to create a weird chip load. It's maybe going to wear down your tool quicker than you want it to be worn down. Delicate cutters are also very stingy about how much chip load they can tolerate. So if one side of my end mill is cutting heavier than the other side, and the other side is cutting lighter, it is likely that I'm going to break that tool because I'm taking too heavy of a load on one side. To keep runout from becoming a limiting factor, it needs to be kept no more than 10% of the cutter's diameter. In my opinion, that's a number that's thrown out there. It's a great number as a general rule, but we just need to be darn near perfect. When it comes to an air spindle spinning at, say, 50,000 RPM, 60,000, 90,000, 100,000 RPM, if you're not spinning almost or completely perfect, there will be an issue, which is why the air spindles, which we'll talk about later, are less than 2 micron in runout at 50,000 RPM. So what are some secrets to efficient and effective micromachining? So now that we've figured out what some of the problems are, let's figure out how to solve them. So my buddy Titan here, I'm not going to play this video because I don't think everyone can hear the volume that comes out based on this Zoom platform. But the significance and importance of high RPM and SFM, so surface feet. What is the significance? What are we trying to generate by spinning faster? So my buddy Titan is explaining that significance. And I want you guys all to envision, and when I was doing this part live, I could see people shaking their heads. And right now I'm sitting in my living room kind of talking to myself. So I'm hoping everyone is going to understand what I'm saying. But imagine back in the day, before all these rules were put in place, when we had those merry-go-rounds that your parents pushed you on or your friends pushed you on, and there was no safety. And, you know, the faster you were pushed, the greater that velocity became. And if you're on that outside edge of that merry-go-round while your parents are pushing you, it is tough to hang on. And that's kind of the fun, right? You're laughing, you might get flung off. The velocity on that outside is way more powerful than the velocity on the center of that merry-go-round. So if you're trying to hold on to the center of the merry-go-round, it's actually quite easy. And what you can do is you can feel yourself being pulled to the outside of that merry-go-round where the velocity is more powerful. So what we're saying is, as that merry-go-round, or as you go to the inside of that force that's spinning, it must spin faster in order to generate the same amount of velocity that's being generated on the outside. So if I have a 5-inch face mill that's spinning at 10,000 RPM, and I have a 20 thou diameter ball mill that's spinning at 10,000 RPM, it's the same 10,000 RPM, but your cutting velocity is going to be so much less for one versus the other, which is why that 20,000 thousandths diameter end mill needs to go 60 or 70,000 RPM versus that 5-inch face mill going at 10,000 RPM. And that's the significance. So how do we care for deflection and cutting forces? Always use the shortest possible tool to maximize rigidity. I think that's pretty self-evident when you get into this small stuff. I have had a customer before give me a 40 thousandths diameter tool with about 5 inches of hangout, and he goes, I want to machine this 5 inches deep. Not at 50,000 RPM, you're not. So rigidity in tool diameter is good. So if you can shrink that cutting diameter down from a larger shank diameter, you're going to create more rigidity, and obviously keep the shortest possible tool and then length hanging out. Tool pass may need to combine roughing and finishing. This depends on what your finish is going to be and how much cutting load you need. That's something to bring up, but I think it's more for the cutting tool guys and the Fusion Autodesk guys. Something I've noticed that I think is kind of cool is conventional milling. Is it preferred over Klein milling with micro machining? And I was in a presentation, a symposium recently in the Midwest over at the Haas Midwest guys. And I was explaining this whole thing about, you know, conventional milling kind of being thrown out the door for so many years and Klein milling being what everyone's utilizing. And I explained how the deflection of the material. So what happens is in Klein milling, the material is going back into the cutting tool, which it has been in many areas of what we've been doing a significant upgrade and change to conventional milling, where conventional milling pushes material away from the cutter. However, by pushing material away from the cutter itself, it reduces the deflection on an already super thin and fragile tool. And so I brought this up, and I found success utilizing conventional milling and micro machining many times. And a customer pulls me to the side. He goes, you know, we do a lot of hard milling, and that's the same thing we do in hard milling, because we need that deflection, that we need that material to go away because the material is so hard already. Any more added deflection just creates problems for us. So keep that in mind when you're doing your micro machining, conventional milling versus Klein milling. Choose the right software. Obviously, we're working with Fusion, and I believe fully in Fusion. What's great about Fusion and Fifth Axis and Haas and AirTurbine all combined is we're already in the Fusion software. And if you need to bring in a vise, or you need to bring in a tool, or you need to bring in an air spindle just for the 3D modeling of your program, it's already there, and it all exists, again, in a symbiotic relationship. There's a lot of massive benefits to Fusion, but I'm not here to sell it. I'm here to educate you on choosing the right software. And by choosing the right software, you'll see massive reductions in cycle time and massive reductions in should I say that reverse, actually? Your tool life will become longer. Your finish will become nicer. And all of this can be done with the right tooling and the right software to go along with it. And then, of course, make sure you clear the chips. Clearing the chips is important. Recutting them obviously isn't going to help an already fragile tool. Workholding, rigidity. We talked about this. I'm going to let Matt Evans, a lot of us call him Mevins, over at Fifth Axis, talk about this more with you. But workholding and that rigidity is just, it's super important. Choose the correct tooling, again, super important. That's what Harvey's here for. And high spindle RPM. We've talked a lot about this as well. So these are significant steps and pieces that need to be applied in order to generate micro machining success. So what are the advantages of high speed? And I've not seen this movie yet, but I heard both good and bad. So I think with everyone on quarantine, I'll give this a go before too long. All right, so advantages of high-speed cutting. Hopefully I'm not boring anyone yet. Hopefully my redundant voice is entertaining enough in my terrible jokes. But now we get into the advantages of high-speed cutting. Increased machine accuracy. And this is kind of a cool thing that I had researched a couple of years ago, and it's kind of neat. And I'm sure you guys are reading it as I talk. But what's neat is as the cutting speed increases, the cutting force decreases due to a theoxtropy, or the property of a material to be work softened due to the sheer strain imparted on it by the tool's cutting edge, and then go back to its original hardness once the cutting process is complete. That's pretty cool. Now, I'm not a metallurgist, but I do appreciate when a metallurgist does his job and applies that information to me, and then I can utilize it while spinning at a higher RPM to create success on my end. Improvements in surface finish, I think that's pretty obvious when you get into, based on what we were saying with velocity and the higher RPM that's required. When you get into that small diameter tooling, you want to get that mirror finish. You don't want to do any of those secondary operations. That high RPM is going to help immensely. Reduce burr formation, I believe that's also obvious based on a better finish. Longer tool life, which we've discussed a lot, and I believe Don's going to help us out with that. Excuse me 1 second while I take a sip of tea. And reduce cycle times. Reduce cycle times, I think, is obvious based on if I'm going at 10,000 RPM and I'm going at 5 inches a minute, and I go at 50,000 RPM and I go at 100 inches a minute, that's obviously going to reduce my cycle time. So yes, RPM can help with that in conjunction with everyone else's technology. So how can the air spindles help you find success? Work smarter, not harder. In an ever-evolving world, which is, I think, something we're all kind of either dealing with, adapting to, trying to adapt to at this very moment, with most of us working from home, some of the most intelligent things we can do have to do with being more clever in the way we think. Not just thinking outside the box, but realizing there is no box at all, and we have to recreate ideas of how we once thought. So thinking smarter and not harder includes everything, but not just air spindles. It includes how we're going to all work together in this new modern world that we're living in. And we're all hoping that we can get back to what we were very soon, but if for some reason it takes longer than we're all anticipating, this creativity will be applied in many fields. And if there's anything that myself or any of the guys that are here today that we're working with can do to support you remotely, whether it be educational or with product or just anything on any aspect, this whole symposium, this whole webinar is created in order to support one another, not to sell products, not to push product placement. It is to say, look, guys, we're all on the same team. Let's do this together. This is a brave new world we're all in, and let's do that. So AirTurbine has been doing this for over 30 years, and it's revolutionized the way high-speed machining has been accomplished from many aspects, which we'll go over. But one of the coolest things is knowing that you can take any CNC machine and make it a high-speed machining center with a couple $1,000s, and that's pretty significant. AirTurbine's backed by a team of highly qualified engineers, and they've created 3 separate lines, one for your CNC mills, one for your turning machines, robotics, automation, and then your hand tools, which is how the company started over 30 years ago. So what benefits are received from this technology? Well, it says compatibility to machine with both speed and power without sacrificing one for the other. And what that means is what I just told you about the CNC machine being instantly turned into a high-speed machining center. If I have all the horsepower and torque that I need in that main machine spindle, but I'm maxed out at 12,000 RPM, and I have a small diameter tool or 2 small diameter tools, and I have to max out my machine RPM at 12,000 for 30 minutes, an hour, 3 hours, 4 hours, that's not a healthy relationship that your machine wants to do. So by applying an air spindle or a higher RPM situation of any kind to your CNC machine, you now don't have to sacrifice speed and power. You can have the speed when it's required by rotating the air spindle in through your carousel, which we'll go over later, in through your ATC into your main spindle. So use all your horsepower and torque as you normally would on your CNC machine, but then rotate in the higher RPM whenever it's required. This way you don't have to dedicate a whole machine just to higher RPM. and you have to have a secondary operation doing this. And this way you don't have to machine for hours and hours, redlining the RPM of your CNC machine. It's a combination of both. It's cost effective. We can go over prices later on if you want to, but again, this is not for me to try and sell products today. I just want to try and educate. Save machine spindle life. That goes hand in hand with what we just discussed about the CNC, where when you rotate in that air spindle, you can M19 your CNC machine, which locks it in place, and only the air that powers the air spindle itself will spin just the air spindle at 50,000 RPM, and we'll have video for that, or 60,000 or 70,000 or whatever you need. But the main machine spindle does not rotate, so you're now saving the life of the main machine spindle. Combine most operations. That's kind of like what we were just talking about secondary operations. So whether I'm taking in, my work piece from one machine to a second machine based on one machine having higher RPM, or my machine just not being capable of creating the finish that I need, so I need someone to hand polish or something like that, all of these combined attributes of higher RPM will help you reduce those secondary operations. Extend tool life. We talked about that a little. High precision, we talked about that a little. Reduce cycle times, we talked about that a lot. No duty cycle of thermal expansion. We're gonna go over this a little bit more with some great documentation, but just briefly, it means that when you run this air spindle, you can run it 24 hours a day, 7 days a week. It's not gonna heat up on you. It's not gonna thermally expand, but we'll go over that a bit more in a minute. What do we do to keep things simple? Now, I think with technology these days, there's often a battle between how great can my technology be and am I able to still make it user-friendly and simple for someone who hasn't taken a course in it. So what do we do to keep it simple? Well, it's easily adaptable. About a 5-minute video where you get to see my ugly mug will show you how to apply this to your CNC machine. Someone who's brand new at using an air spindle, it might take them half an hour and a removal of fear, because I think a new anything is something that we kind of shy away from sometimes. So creating that confidence in what you're about to do, and about 15-20 minutes of installation, and you will easily be adapted. Zero maintenance. That means there is no oil, there are no brushes, there are no gears, there's nothing that you have to worry about maintaining over time. You just use it for the lifetime of the bearings themselves, and then you go for a rebuild and do it all again. There's no maintenance on this thing at all. Patented cover up to 1.4 horsepower. Typically when you get into micro tooling, torque and horsepower aren't the #1 topic of discussion, based on the fact that I'm running, say, a 10,000s, 20,000s, 30,000s diameter tool. All I really need is RPM. However, I'm going to go over an exact company to company test that was done over in Korea here in just a little bit. That's going to show you what that difference in horsepower can do in the micro machining world. So we'll go over that a little bit more in a minute. Thermal expansion, we've talked about that, and it's super quiet. It is under 78 dBA. A lot of times in these machine shops, you can't even tell they're running. It's not a first time for me to plug it into a machine and somebody looks at me and goes, "Did you turn it on yet?" And they actually want to touch the spinning cutting tool at 50,000 RPM to make sure it's spinning, which is a liability. Don't do that. But they're incredibly quiet, and that's going to be a benefit as well. You won't be able to hear the volume on this video, I don't believe. If you can, that's fantastic. But what this is showing is how the turbines themselves, this patented technology, how it creates the torque and the horsepower that AirTurbine has been known for over 30 years. And if you notice, that's the inside of the product, right? It is simple as can be. And the way that turbine works is as the air goes in, there's some internal technology, let's say, that expands and contracts an O-ring to accept more or less air, which keeps this thing, when it's under load cutting material, it keeps the RPM within 5% of that rated whatever RPM that you order. So 50,000 RPM. And what's going to happen is as it's under load, that O-ring is going to expand to accept more air into the turbine, which is going to keep it at that same RPM the whole time, which is something that is going to be extremely powerful while programming. Because if my buddy Jack over at Fusion 360 is doing some programming and he put into the software 50,000 RPM, 300 inches a minute, and as soon as I touch material, I'm actually at 35,000 RPM instead of 50,000 RPM, then all those calculations for my software are going to be incorrect, which in return is going to have a domino effect of what my finish is going to look like, what my tool life is going to look like. So the patented technology of this turbine is incredibly significant to the overall success that you're going to have. Here we have what that power can do. So these are my buddies over at Doosan, my buddy John. I hope he's doing all right over in New Jersey. We're doing some tricoidal milling here at 40,000 RPM, but we're cutting Inconel with a 6mm, 6-flute Kennametal ceramic tool. Sorry, Don. I'm working with you. I love your tools, but I have to be honest with what we're using here. So this was a Kennametal tool, a ceramic tool that was cutting Inconel. And this is the max capacity of what an air spindle shank diameter that it can hold. And at 160 thousandths deep and 40 thousandths RPM and an advanced rate of 190 inches per minute, we were able to quadruple the tool life of that ceramic tool cutting Inconel. And Inconel, as most of us know, with the high nickel content, is incredibly hard. So most high-speed alternatives out there don't have the capability to really put a dent into these harder materials, and this is just kind of showing you guys that the AirTurbine product can. So I don't know if any of you guys can read the Korean on here, and I hope it doesn't give away the competitive product that we were going, or products that we were going against. But what I want to show you guys is what that power can do. And we were working at a customer in Korea, and we were going head to head with a couple other companies, and all of the parameters were exactly the same. We all had 50,000 RPM. We were all cutting the same steel. We all had the same depth of cut. We all had the 1mm or 40 thousandths diameter ball mill. Everything was apples to apples in the test. So in order to be more successful than a competitor, what's the only thing that can be changed? Well, the only thing that can be changed in a situation like this is the feed rate. And the only way you can change that feed rate is if you're able to keep your RPM, torque, horsepower while under load. And so what happened was, if you're looking in the bottom right-hand corner, the competitive companies were at an 8,000 millimeter a minute. And I apologize. I know a lot of you guys are inches, imperial system here in the US, but also around the world where we work with a lot of companies. And if you want to translate it, you're welcome to. But 8,000 millimeters a minute was the max feed rate that the competitor companies could do. And we at AirTurbine were able to go 12,500 millimeters a minute. I know that says 11,000, which was the sweet spot, but 12,500 millimeters a minute, which was the max that that machine could do, in which case the cycle time was reduced by about 30% or so. If you look at cycle time on the left-hand side, fourth from the bottom, 6.5 hours to 4 hours, just based on the capability to have a bit more power, which allows you to go through the material because you don't want that RPM to drop while you're under load. It's incredibly important. Here is just a little bit more about that precision of 2 micron or less. Little video showing tiny jiggle. So friends in Korea, again, these guys are precise. I love them. So when you get all of these attributes together, your rigidity, your tooling, your programming, your RPM, what can be accomplished? So here in Korea, we were machining hard steel 0.07 millimeter tool diameter, which I believe translates to about 2/1000. And we were able to reduce the cycle time per hole of 30 seconds to 13.5 seconds per hole. And this customer had thousands of holes, and I was told that the overall cycle time for one of his jobs was 32 days, which with this new hole per second cycle time, took his 32-day cycle time down to about 15 days of cycle time just by adding RPM, making sure that the tool was rigid as could be, the run out was good. But this is some of the success that can be created with higher RPM. 2/1000 in diameter is not going to be possible without really tiptoeing through a program. So we talked a little bit about thermal expansion, right? And the fact that with longer programs, whether it be a machine spindle or anything with gears, longer programs are going to cause the components on the inside to heat up and expand, and too much heat will actually break them down, which is why in a lot of situations you have to have brakes from your CNC running at higher RPM because it needs to cool off. It's going to break down and expose the weaknesses of the machine itself. So with AirTurbine, being that it's so significantly simple on the inside, you don't have to worry about that thermal expansion. And a test was done by our friends in the UK called Technicut. Technicut is an amazing company that makes their own tools for the aerospace world. Technicut decided that they wanted to run a test with our products and with AirTurbine's products. And what they found was that after an initial heat up, it remained the same temperature for over 12 hours. What else that was found, and you guys can read this, I'm sure, says the maximum change of thermal expansion was 9 micron, which was taken after 10 hours. However, the small increase towards the end is due to the buildup of cutting edge, which was observed at the end of the test. So what happened, because I was on the phone with these guys, a great group of people, the titanium that they were cutting actually started to stick to the end mill itself. And due to that, that's where 8 micron came from of the overall 9, and only 1 true micron of thermal expansion after 10 to 12 hours of straight running. So tool mounting, tool changer mounting assembly, that's what we call a TMA. A lot of people call it a stop block. As you can see here, it's about to tool change out. One of the most popular questions we get is, do I have to manually load it and unload it? Can I put it through my ATC unit like everything else? You absolutely can. It's part of keeping it simple. It's part of making sure that we're not adding any cycle time to your already reduced cycle times that you're trying to have. So absolutely, this goes through the ATC of any of your CNCs, and that way you can use your main spindle as it should be used for power and torque, horsepower. And then when you need the higher RPM, you just rotate it in quite simply. There are a few different ways. I'm gonna have to skip this video because I don't think you guys can hear the volume. But there are a few different ways to power the air spindles. And so you can power them by utilizing through spindle air, which is air through the back end of the tool, super simple. You can use a manual connect and disconnect through the side, which is a little bit slower and goes back to, you know, kind of having to manually load and unload, or our patented TMA block, which we just discussed, which allows you to then go through the TMA like any other tool. And so as far as technology, what are we continuing, what is AirTurbine continuing to do to make your life easier? Well, new product is a 90-degree spindle. A lot of people get excited about this. It's what's great about a Haas machine, and many of the other machines, of course, but as you can see, this is tested on a Haas machine, is if I do an M19P and then pick a number, I can rotate that 90-degree tool at anywhere in the 360-degree area. And then it goes right back into the tool changer. Through spindle coolant. So recently released is the through spindle coolant. So if you're doing a lot of drilling, if you're having trouble evacuating chips, the same powerful air that goes through the side of this tool, as you can see in this video, is still constantly applied, but now we have a hollow shaft that allows the coolant to go through the back end, which allows you to drill a lot faster, have the longer tool life that you're looking for, remove chips, reduce cycle times, everything that's the benefits of a through spindle coolant tool. Something else that's kind of exciting for us is variable speed. So for over 30 years, AirTurbine has been known as one powerful fixed speed, and it's not going to reduce while under load. All the sales guys, all the engineers, it's something we repeat all the time. However, recently released at EMO this past year, 2019, is a variable speed tool. And you can see in the video how that speed is going forward and back, or how that speed is able to be changed. There's a lock nut that kind of slides all the way forward and slides all the way backward. And so what happens is when it slides all the way forward, you're using one turbine, and that one turbine is spinning at either 30,000 or 25,000 RPM, depending on the tool. And then as you back that nut out, you're activating a second turbine, and that second turbine allows you to go at a second speed of 50,000 or 40,000 RPM, depending on the tool. So now you have that option that a lot of people are looking for of a variable speed tool. Working with the Philips team over at Haas, also a great group of guys. They developed the Philips Machinist app. And if you guys don't have an app to help you with your calculations of programming, we highly recommend utilizing this one. It's a good one. It's a great one. And what's beneficial to AirTurbine is if you're programming or putting in numbers that are going to require a higher RPM, if you're going to be trying to machine at a faster speed, it will automatically take you to the AirTurbine website, where you can then pick what's required for your tool, for your end mill diameter, and for your material. You can be directed to the exact area that you need to find. So the Philips Machinist app has been a huge benefit to a lot of customers. If you haven't downloaded it, I would recommend it for many reasons. So I'm going to quickly go over, because I have no idea what time it is, and I know I talked a ton.
We're at a little bit over, Tony, just a heads up.
Awesome. You're all right, Rob. I'll speak like I'm selling cars or something. All right, so this is significant because most people don't realize how quickly you can make money, and I'm gonna talk quickly, and if I repeat that, obviously it makes me talking slower. So let me go ahead and skip ahead. All right, so shop cost per hour. Most people calculate shop costs at about $100 to $150 an hour, electricity, all that kind of fun stuff, right? So I've minimalized how much money can be made through the cost savings of cycle time alone, just the cycle time. So 8-hour shift, 1 shift per day, 5 working days, that's a normal thing. 1 machine, not a bunch of machines. The original cycle time of 34 minutes, new cycle time of 6 minutes, not hours and hours of time reduction. And yet on 100 pieces, there was $7,000 made. So a tool can pay for itself extremely quickly, which is part of that working smarter and not harder thing. See if this thing lets me skip ahead. So here's another one. We'll go over it real quick as we just did the last one. Pretty much all the same parameters. Original cycle time machining in graphite was 42 minutes. We reduced it down to 24, which at 500 pieces was $22,000 of savings, only on cycle time. And although I'm doing another $20,000 savings here on a soap mold, I don't want to be too redundant. And thanks to Rob, I actually know what time it is. So we're going to skip through this one, but you can see cycle time was saved again. Thank you for learning. I hope this has been somewhat beneficial. And if you have any specific questions about the products, please let us know.
Tony, there was one in the chat. It was asking about how AirTurbine Tools, how does it save spindle life? If it's not rotating the spindle.
So the main CNC spindle is going to be saved, because if I was originally running, say, a 40 thousandths diameter end mill, and my max RPM is 10,000 RPM, that's really the only way that I'm able to run that 40 thousandths diameter spindle, 40 thousandths diameter tool, is by maxing out the RPM of that main spindle. So if I'm running at 10,000 RPM for 2 hours, and then instead now I'm putting in an air spindle that runs at 50,000 RPM, and the main spindle does not move at all for that same 2 hours, the machine spindle life is being saved for that same 2 hours of duration, which is probably now going to be more like 20 minutes. But that main machine spindle is now not being used for that 2 hours of max RPM on that CNC machine.
Hope that makes sense. Anyone else with any, leave it for a minute if anyone wants to chime in on the chat or unmute and jump in. Otherwise, going once, going twice. We'll just, I guess we can hand off to Jack now and let Jack will jump in a little bit. Oh, one more question or comment. I don't know if you see the chat here.
Says
Tony.
Turbine Tools, it said needs to be rated for bearing lubrication. I don't know that AirTurbine specifically has ever re-lubricated a bearing, and that could be another company where lubrication needs to be applied. If it happens to be an AirTurbine spindle and I'm confused about how I'm reading it, it would just mean that it needs to come in for a repair, and those bearings get replaced, and it's a brand new tool again.
Cool. With the sake of time, or one more.
Collet types. AirTurbine Tools uses ultra precision ER11 collets. This 300 people watching this webinar and being able to type a bunch of questions really shows our level of knowledge, doesn't it?
Yeah, put you on the hot seat. All right, we'll transition in the sake of time. We'll transition to Jack, and again, any other questions for Tony? We'll hold off just to the sake that we get all the presenters through, and then we'll open it up at the end, because we'll make sure that we get everyone's questions answered. So with that, Jack, if you don't mind taking the screen share, and I'll turn off. Okay.
Okay.
Gotcha.
We see that. Try and get this out of the way. That's best. I'll do it down here. Brilliant. All right. So can you see that and hear me? All good.
Gotcha.
Fabulous. All right. Well, hello. Good morning, good afternoon, good evening if you're over on my side of the world. Yep, so my name is Jack Holmes. Ooh, what is this? And I am that was you throwing a poll at me, trying to throw me off. I'm a technical consultant with Autodesk, and just over the next kind of half an hour or so, I'm going to discuss with you how we can use high-speed machining with a focus on Fusion 360, which is one of our software packages. Oh no. There we go, cool. So quick agenda of just what we're going to go through. So we'll start off by looking at actually what is Fusion 360. Maybe everyone on this call isn't already aware. So we'll quickly run through that. Then we'll have a look at a general kind of Fusion 360 CAD/CAM workflow, so that we can then go on to understand how we can use high-speed machining within that. So that will involve looking at adaptive clearing, looking at how we can use the air turbine spindles with Fusion 360, and how the kind of joint workflow for both of them together works as well. So like I say, we'll start off quickly by looking at exactly what is Fusion 360. I'm guessing not everyone on this call already knows. If you do, then hopefully you'll learn something new. So Fusion 360 is one of our software packages at Autodesk, and it is our integrated CAD, CAM, and computer-aided engineering tools. So it's got a whole range of capabilities all wrapped up within this one package. It's a cloud-based platform, which essentially just means that your data is saved to the cloud. So when you save your projects and files, they get saved to your account online, meaning that you can access your data from anywhere. So it works a little bit like a email account, for example. You can log into this account on multiple devices. So you can log in on your computer, or work on tablets and on phones, and you always have access to your data through the cloud. It also means that collaboration is made much easier, because you can share your projects, work on projects with other people, all through the cloud as well. So within Fusion, there are a number of what are called workspaces, which are the different environments where we can perform all of these different capabilities. So we've got workspaces for doing designing work, for doing manufacturing, for doing 2D drawings, simulations, rendering, animations, and the latest addition, which was put in kind of a couple months ago, was an ECAD workspace as well. So that's an area for doing electronics work, so for designing and creating PCBs and all that kind of stuff. So we'll have a closer look at some of those workspaces now. So the first one we're going to have a look at is doing solid modeling. So within the design area, we can create 2D sketches and then use tools such as extrude and revolve to take those 2D sketches and turn them into 3D solid models. And then on those 3D models, we can apply various features such as fillets and chamfers. We can put draft angled faces on there. We can add extra material on, remove material, etc. All of the kind of standard CAD tools that we'd expect, really. When we set these up, we obviously kind of dimension the various features and items, and we can link these dimensions together as well. So that means, for example, if we make the diameter of circle 1 relative to the diameter of circle 2, when we change the size of that first circle, the second one will automatically update. And if we're clever about it, we can kind of set up the whole model so that everything's linked together. So just by changing one dimension, everything will kind of scale and adjust accordingly. As well as solid modeling, we can also do what's called sculpting in the design space as well. So this works rather than being based off kind of dimensioned 2D sketches. It's a much more kind of free-form style of designing and working. So you'll see here it's based off kind of manipulating surfaces, manipulating the vertices and the nodes, it's called, of these surfaces by sort of dragging them around, rotating them, scaling them in a much more kind of organic freeform way, I guess. So it does work. You can kind of imagine it similar to sculpting clay or something like that. It's much more just sort of visual based than entering specific dimensions or anything. The models that we get out of here, once you're kind of done with your sculpting work, can be used in exactly the same way as the solid models, so we can still apply fillets, chamfers, etc. And we can switch between the two just by changing literally the tab that you're in on the design workspace. So on top of these two, we've also got sheet metal design. So this is, as the name suggests, a way of designing our sheet metal parts. So we can kind of create our 2D layout for these. We can put in where the folds and bends are. We can put in the cutouts, and then fold those into the finished form. And we can do this all as part of our the rest of the model and the assembly as well. So we can do it in place, around our solid models, around our sculpted models, to make sure that everything fits together as it should be. And that's kind of one of the big benefits of having this integrated system, is that we can swap back and forth between these different environments to make sure everything is linked and lined up as it needs to be. So as well as our design space, we've also got the manufacturing workspace, and I'm guessing that's what most people on this call are most interested in. So we can take our models, whether they're our solid models, our sculpted models, our sheet metal, and bring those over to the manufacturing workspace. And again, we do that pretty much with just the flick of a switch. We just kind of choose our workspace from the drop-down list, and it will bring us into this manufacturing workspace instead. And in here, we can carry out milling operations, turning. We can do cutting, so that's things like laser cutting, water, plasma cutting to do our sheet metal parts, for example. And we can also do additive work as well, so 3D printing. For the milling work, we can do everything up to full 5-axis simultaneous. And for the turning, we can do kind of a combination of the milling strategies as well, to do turn mill rather than just your standard operation. Within here, you've basically got a number of different kind of strategies depending on the operation type we're going for, whether it is milling, turning, etc. And then as we can see, you kind of apply your toolpaths to your model. You can simulate these toolpaths and then run this on your machine in the real world. On top of all of this, we've also got simulation. The simulation will allow you to simulate stresses and loads. We can simulate thermal stresses. We can simulate modal frequencies. You kind of see in that pop-up there all of the different types of simulations that we can run. So you can take your part that you've created in the design workspace and simulate this in the environment that's going to kind of be applied in. This then gives us, you see the kind of color map that shows you stresses, deflections, even the factor of safety and kind of criteria like this, to make sure that it's going to hold up to how it needs to act. And the fact that this is all tied together means that if you do need to go back to the design of the part, it's very easy to, again, flick of a switch, jump back to the design space, make some modifications, so maybe add a bit more material on to stiffen it up. Maybe it's been over-engineered, so we can cut a bit of material away. Back into the simulation, run it through again, make sure it all looks good, and go through that iterative process very easily as need be. There's also an animation workspace. So we can see here, you can take an assembly of parts that have kind of relative motion to each other, and we can animate this. You could also take a stationary assembly and do, for an example, a exploded view of how all of these parts come together and assemble. So this area is really useful for kind of creating a visualization of your parts before you actually go and manufacture them, to just express how they're going to look, to check for maybe collisions or clearance issues, as well as kind of design for assembly issues as well. You can make sure that everything is going to fit together in the order you expect it to. And you can check it all here in the software again before actually going and making these parts and realizing there's an issue after you've spent hours producing them all. There's also the rendering workspace. So what this allows you to do is apply materials to your part. You can set up kind of lighting effects and backgrounds and set up the shadow effects and things like this. And it will then allow you to create these photorealistic images of your parts, of your assemblies. Again, a nice way to represent what things are going to look like inside of the software before going and manufacturing them. And it's a nice way to get the point across before those parts are produced. The last thing that I'm just going to talk about briefly is the drawing space as well. So we've got all of these design tools and design areas. You can then take these modeled parts and bring them into the drawing space here, where we can then go ahead and create some 2D drawings of these. So you can drop your parts onto the kind of page templates, as we can see an example one here, and basically create yourself very easily some engineering drawings of these parts. And these are really easy to make. You basically just drop the views in. We have one, what's called the parent view, and then we can do projected views off of that. So wherever you move your mouse to, it will automatically do the correct isometric view for you, and we just click again to drop it in, and all of that's taken care of for you. We can also add dimensions onto here, and those dimensions are linked back to the kind of solid model itself. So if you were to go and change the size of a hole, for example, that you've dimensioned, you'd see that dimension change in the drawing here. And again, a big benefit of having all of this kind of integrated together and all linked together, that if you change the data in one of these workspaces, all of the relevant data is updated in the other workspaces as well. And then also in the drawing space, we can add on things like bill of material, extra comments, and fill out our the drawing information down in that bottom right corner there. So that was the majority of the workspaces we've got in Fusion. There's actually a couple extra, but those are the main ones we'll focus on for now. But like I said, Fusion 360 is a cloud-based platform as well. So with this, you get something called Fusion Team, which is basically the area that you save your data to. So we just throw a quick flash of it there. You can see at the minute that it makes it very easy to share your files and share your folders of work with other people. They can all get access through this Fusion Team area, which makes it nice and easy for collaboration. It ensures that everybody is on the latest version. If one person makes an edit, then everybody else has that instantly. So there's no issues of different versions getting emailed around. Leave comments of the work that you've done so everybody knows exactly what it is you've changed, etc. The Fusion 360 is really the kind of convergence of design and manufacturing capabilities. It puts the data at the center, which just means that everybody involved in that design and manufacturing process can get access to that data at every stage of that process as well. And Fusion 360 can be used at every stage of the design and manufacturing process. So from scoping out the job to obviously doing the actual design work, programming the part in the manufacturing space, through to then running it on the machine, even doing the inspection on the part after it's been created. So within the manufacturing workspace, there is also some probing capabilities, making sure that that part gets all the way through to actual use. Okay, so hopefully everybody is a bit more clear of what Fusion 360 is. As you can see, it does a lot, so we don't really have time to do a kind of deep dive of every single workspace, but there's just a bit of a whistle-stop tour of its capabilities there. So we'll have a look now at the general kind of Fusion 360 CAD/CAM workflow that you'd usually go through, so we can then understand how high-speed machining would fit into this. So the first stage is to either create your CAD model, but obviously you're not always creating your own model that's going to go and be machined. Sometimes this is given to you, or it's just an old model that was made a while ago. So it's also worth noting that Fusion 360 will also import kind of all standard CAD formats really. So whether that be IGES, STEP, Parasolid, etc., you'll be able to import them all in if you're not creating the model yourself within Fusion. The next stage is then to define our job setup. So this is where we define the stock material. You position your coordinate system to link this up with where you create this on your machine tool, and also where we define the operation type as well. So this is where we set if we're going to be doing milling work, turning work, cutting, etc. We can then go ahead and define the operations. So there's a number of different strategies for tool paths, depending on whether we're doing milling, turning, and then within there are different strategies for if we're doing roughing tool paths, whether we're doing finishing on surfaces. There's also some different cycles available for drilling and some kind of more specific tool paths for things like chamfering. So obviously which one we choose and which one we define depends on what it is we're trying to cut, the part itself, and then the features on that part, as well as the actual stage of the machining we're at. So obviously when we're roughing, we'll use different tool paths to when we're doing the finishing work. After we've created our toolpaths, we want to go ahead and simulate those. So we can simulate with the stock. So we can ensure that we're cutting away enough stock in the correct places. We can check for any collisions or gouges that might be occurring so that we can fix them at this stage in the simulation rather than discovering the issue on the machine tool itself, which is obviously going to cause problems later down the line. Once we're happy that everything looks good and we've got all of our toolpaths in there and the simulation is showing no errors, then it's time to obviously create our program. And for this, we obviously need a post-processor file to make sure that this is going to work on our relevant machine tool. So all of the post processors are available for free with Fusion 360. So there's a whole library of these online, and you can see this link here will take you to that library from within Fusion. It can also be found just with a simple Google. And there's also about 100 posts that are installed with Fusion as well. So it makes it very accessible to be able to kind of take your programs from Fusion actually onto your machine. Okay, so now we understand a little bit about the Fusion 360 CAD/CAM workflow. We can look at how high-speed machining is actually going to fit into this process. So obviously, because it's to do with machining, it's going to fit into that stage of the process. We can't really change anything in the design. It's things that we're going to do on an operation level where we're going to be able to use this high-speed machining. So the first way that we can do this is in our roughing stage. And this is by using something called adaptive clearing. So adaptive clearing is a method of essentially clearing material as quickly as we can, which is exactly what we're trying to do, well, not only in the roughing stage, but throughout the entire machining process. And it works by keeping a constant load on the tool at all times. So the toolpath will kind of flow around your part to ensure that this constant load is on the tool rather than a varying load throughout the cutting process. The best way to use adaptive clearing is to use the full length of the tool, so to cut with all of the flute that you have basically, and do this with a small step over. So we're taking kind of small cuts in width, but full depth cuts. This will clear material quicker, which will obviously then lead to a decreased cycle time. As well as decreasing the cycle time, we're also going to increase our tool life as well, because this method is actually kinder on the tools, because we're keeping this constant load and because we're spreading out this load over the tool as well, rather than sort of more traditional cutting methods of using the full diameter of the tool but with quite a shallow cut. We're spreading this load out over the full length of the tool, which is going to increase its life. So we're getting shorter cycle time, longer tool life within those cycles. So very much a win-win situation here. So then within Fusion 360, in the manufacturer workspace, in the CAM area, we've got a 2D and 3D strategies available to do this adaptive clearing. And which one you choose just depends on the kind of geometry that you're trying to machine. But essentially, both of these will kind of look at your model and automatically work their way around it to use this adaptive clearing. And because they just pick up the model, very little input information is needed really. So as long as we make sure to use this small step over, but give it the full length of the tool to cut with, then Fusion will sort of take care of the rest there. And really this is the kind of go-to roughing strategy. So I know most people, myself included, whenever you start programming, it's always the sort of go-to first operation that you put on is an adaptive clearing toolpath, just to clear that material as quick as we can and effectively as we can as well. So we've got a couple of little animations just showing this in action here. So on the left, we've got the sort of traditional pocket clearing strategy, and we'll see how that follows the outer shape of the pocket. And we can see below that how it's using full diameter of the cutter, but with quite a shallow cut represented in the red highlighted area there. And then on the right, we've got our adaptive clearing. So we can see that kind of flowing around, getting into the corners there as necessary, using full flute length and small step over. And we can see how that very quickly works its way around that pocket to clear it out. So there's just a very quick video of the adaptive clearing actually in action on the machine. So we can see on this part, small step over, fairly deep step down there. Actually, in this case, we're not using the full length of the tool. Obviously, sometimes this will depend on the geometry that you're trying to cut. So if we're not actually cutting down far enough to use the full tool length, then that's not going to be available. But where we can, as much of the tool as we can use as possible is what we're trying to do. All right, so adaptive clearing is a very effective method for our roughing stages. But we also want to be able to speed up our finishing stages as well. And just like with roughing, obviously what we're trying to do here is clear material quicker. That's the whole aim of this high-speed machining, essentially, is just to, cut through this material as quick as we can. Unlike with the roughing, there isn't one specific strategy that we can do this with. Because of the nature of kind of finishing work, it's very dependent on the features that we're trying to finish, the particular surface that we're finishing, and the areas that we're trying to cut.
Hey, so, Jack, just really quickly jumping in, one unconscious of time, we need to continue to move along a little bit. Just a heads up.
Cool, no worries. I'll whiz through. Yeah, so if we can't change the actual operations, what can we do? We can, this is where our air turbine spindles come into place. So obviously, Tony's kind of spoken about these, so I won't spend particularly long, especially as running out of time a bit. But this is where we can use our air spindles to increase our spindle speed, therefore increasing our feed rate, therefore bringing our overall cycle time down. And quick video here. You've kind of seen this in action, so I won't linger, but we can see a couple examples of taking that one down from 30 minutes to 5 minutes, 1 hour down to 10 minutes, and so on. If you want to see any more of that, I think there's plenty of videos I'm sure Tony can send you. All right, so we'll just have a quick look now to finish up at how we can use Fusion 360 and air turbine spindles together to get the most out of both of them. So luckily for you, we've made it very easy to do this, and I'll just run through that workflow now. Okay, so the first thing that you're going to want to do if using Fusion 360 and air turbine spindles is to import the air turbine spindle tool library into your Fusion 360 tool library. So this will basically bring in the air turbines as holder models, which will then allow you to assign these to the tools that you're going to cut with. And these will have some information associated to them so that Fusion will pick up that you're using this and basically output the relevant code. So that's nice and easy to do. You just need to right click on your local library, hit import and find that relevant file. Now at the minute, we're just giving these files to people as requested. So if you do want to do this, let one of us know and we can pass that on to you. Yeah, but once it's in there, it'll kind of be in your local library in Fusion for good, so you'll have that available to use with all of your projects going forward. Once it's in your library, you're then ready to set up your tools. So this will be done same as normal. So we can define tool length, tool radius, all of that kind of stuff. We just want to obviously make sure that we are selecting the holder and using one of your air turbine spindle holders, the relevant one that you're going to use, linking that up with your tool to make sure that that is going to be used both to give you the correct code and also just for the kind of simulation collision purposes as well, just to be as accurate as possible. Also, when we're setting up our tools, we want to define our speeds and feeds. And obviously, the reason why we're using the air turbine spindles is basically to give us higher spindle speed, therefore higher cutting feed. So the best way to kind of calculate this, if you don't have the info already, is if you make a note of your feed per tooth value, because this is what we're kind of trying to keep the same here. It's all well and good up in the feed rate, but if we go in too quick, then we could damage the tool, damage the part, get a poor surface finish and all this kind of stuff. So if you make a note of your feed per tooth value, as it is with your kind of standard spindle, and then input your new spindle speed. So in this case, we've gone with the 50,000 RPM, and you'll see your feed per tooth value automatically change in the library here. So if you then go in and manually change that back, you'll then see the cutting feed rate update instead. So in this case, the feed rate has gone up to 10.5 meters a minute, which was considerably higher than we were using before, which is obviously in turn then going to give us the ability to kind of bring down our cycle time then. So once you've got your tools set up, you can then go ahead and define your operations as you normally would. Obviously, just making sure to grab your tool that has the AirTurbine spindle with it for the relevant toolpaths. And like Tony mentioned before, the AirTurbine spindles can kind of go into your tool changer. So we can mix up the operations that use the main spindle with operations that use the AirTurbine spindles. And we can output all of these as one program at the end. An extra and kind of optional step when defining the operations is setting the coolant type for each operation here as well. And this is to do with, again, what Tony mentioned earlier about the different ways that you can have your AirTurbine spindle installed. So some people kind of link theirs up to the air blast output and then use the on and off M codes for this to turn their air spindle on and off at the start and end of the operation and program as well. So if that is something you want to do, the best way to do it is just by setting the coolant type to air in here, and then the post will kind of take care of those M codes for you. So then once we've got all of our operations in place, again, we're ready to post-process and get our NC code out. And for this, you're going to want one of the modified posts that we've got just to output the correct code for you when using these AirTurbine spindles. So just like the tool library, we're just handing these out at the minute as these are asked for. So if you do want this post with the modified ability to use the AirTurbine spindles, then let us know. At the minute, we've got posts for Haas machines and the Fanuc Robo Drill. If there's any other specific machines, then let us know and we can kind of look into creating a modified version for that as well. Okay, so I'll just add a bit of quick video here. I'll fly through this if we're short on time. So we can just see our AirTurbine spindle in action here after being programmed with Fusion. And same again here, just a quick video without the coolant. So we can see our little Han Solo being machined there at a much higher feed rate. Okay, so that was pretty much it from me. The last thing I just wanted to mention is that if anybody wanted to give Fusion 360 a go, we actually have an extended access program on at the moment. So usually there's a 30-day free trial available for Fusion. We've extended that due to the kind of current situation, really, because of all of the COVID stuff, just to make it easier for people who are transitioning to working remotely, working from home, making it easier for people to kind of pick up and be able to carry on working. So at the minute, we're offering a Fusion 360 for free up until the end of May. So if you did want to give it a go, you've got just under 2 months to kind of get to grips with it. And hopefully it will kind of help you in these strange times working remotely. So that was it. Thanks a lot for listening. If there's any questions, feel free to shout out. I've seen that the chat is sort of lighting up, so I'll have a look at that now. Otherwise, thanks very much.
Jack, thanks again. And I realized looking at the schedule to apologize to you and Tony. You guys were actually spot on. I was ahead. So you ended right 2 minutes shy. So if anybody, we have time. If there's questions, feel free to ask. And, I just want to reiterate what Jack was saying about the extended access program, because that's it, to us. It's how do we continue to keep the world of manufacturing moving forward? Because we don't want to see everything just fall off. So whatever we can do as far as Autodesk is concerned, we are converting our sales team to more of a customer adoption team. So if there are customers who are struggling with not having access to the tools they normally have access to, feel free. You are able to use Fusion. We are trying to help customers continue to keep the world of manufacturing going. That's the intent and purpose for that. But it is online. It's free. It's available. There's online content if you're looking just to continue working in these weird circumstances that we have right now. But yeah, please feel free to reach out if you have any questions on that. Cool. Yeah. That's a great point. Jack, would you mind adding the extended access link to the chat so everyone has a chance to?
Yeah, definitely. Yeah. Sorry, I meant to say, yeah, you can follow that link, or I'm sure if you just Google Fusion 360, you'll quite easily find your way to it. But yes, I'll drop that in. There it is.
Great. We were going to take this opportunity if anyone wanted to take a quick stretch, unless we're ready to go. If everyone wants to kind of just hammer through it, the next presenter is actually going to be Matt at Fifth Axis. So if Matt, if you want to roll through, we can just keep going. Let me allow you to unmute yourself first.
There we go.
There
Am I
you go.
muted?
Yeah, you're good.
Yeah. Is everyone good to go? I'm cool to go if you guys. We'll just keep cranking through it.
Yeah, let's go.
It's raining here in San Diego, if anyone was curious. So it's
yeah.
I'm not going outside. I got nowhere to be. Not going to the beach. Can't go to the beach. All right, let me Let me pull this up. Yeah.
Coming as a guy calling in from Seattle, I don't feel for you at all, dude.
I think I know who that guy is.
Yeah. Deal with a little
Same
rain.
here for the UK. I don't know what's going on.
All of you guys, I know.
Yeah.
Like 8 months of rain, man.
Right.
It's awesome.
Let's see here.
Thanks for checking in, guys, with the location poll. Just good to know that we have an engagement across the the globe actually on this call. So if you like what you see here and you want to see more content, we're happy to start putting together more stuff like this. So just keep us in the loop. Let us know. And you're good, Matt. I can see your screen.
Nice. This is going seamless, guys. Cool. Awesome. Well, thank you all for being here. I, appreciate everyone taking the time. Again, this is kind of new for all of us, but pretty cool that we can get us all together. And my name's Matt. I work for Fifth Axis. We're based here in San Diego, California. Very close with Autodesk, AirTurbine, Harvey. So thank you guys for giving me the opportunity to speak on just a couple subjects today. Let me quickly jump into just a little bit of who we are, mainly because the name Fifth Axis, everybody thinks immediately multi-axis machining, which was true. When we started the job shop, we were strictly a multi-axis job shop. But as we've grown, we've got, you name it, 55 3-axis machines, a bunch of horizontal machines. So the company is, all encompassing 3, 4, and 5-axis. The product line, the vices, the fixtures, everything that we do that I'm going to discuss in a little bit is really geared towards 3, 4, and 5-axis. Horizontal, vertical milling is sort of that's our sweet spot. That's what we do. We tend to do a lot of small to medium size components. So that's why there's a really good fit with, AirTurbine and stuff that Harvey does. We tend to do that sort of small to medium, whether it's low volume or high volume production, our sort of sweet spot is small to medium components. So we don't do any large components. That's just not our sweet spot. But this is an image of one of our buildings in San Diego. So we started off doing aerospace, a lot of medical defense. So all of the products that we've created came out of necessity for, really aerospace and defense contracts. Being in California, everything's expensive. We had, we had to be efficient with everything we do, the programming to the tooling to the setup. So that's what drove really sort of the whole direction of our shop. And we started in one small building, and now we've got 5 buildings, 160 employees. So we've grown very quickly, and we've been able to use a lot of the sort of the techniques that we've talked about today, from the the programming and the tooling to help get us to where we are. So there's a couple things I wanted to talk about just briefly. My presentation's like relatively short, but the couple things I wanted to talk about first and foremost was a little bit about quick change. So a little bit about our system, but just quick change in general. And I really kind of want to focus on a couple key things that have to do with Fusion and some advantages that you don't always think about right off the bat. Obviously, there's some obvious benefits to quick change, but there's some other like really nice advantages to using any quick change system. Then a little bit about part density, which again sort of ties in all together. Our goal is to keep our machines running as much as possible. Limit the loading, unloading, allow operators and / programmers to be as efficient as possible. We try and have the machines running as much as possible with the least amount of interaction, because that's when we're making money. So I'll talk on that a little bit. And then last but most important, is really some key things about rigidity and some of the common questions we get a lot about not just our product, but similar products that are sort of smaller footprint work holding, and kind of taking what people are used to in traditional work holding, and how the smaller footprint is, you can achieve similar outcomes, but you have to look at it a little bit differently because it's a different approach. So let me jump right into it. So right off the bat, the first thing I wanted to just touch on was quick change, right? Setup times and changeover times we look at. So when Tony was talking about, looking basically, drilling holes and saving time there, we look at that, we look at our tooling, but we also look at, how long does it like realistically take to set up a machine? How long does it realistically take to change over a machine, it can be difficult to like accurately track that number, especially when you've got bigger shops. It's hard to, really gauge how long that changeover setup time takes. And then there's definitely when we're quoting jobs and we're, looking at, okay, how much does this part actually cost us? The setup and changeover time is kind of that weird gray area where we've got a rough idea, but it may not be a true representation of how long it actually takes. And then that gets amortized over every part we're making. So, we're seeing setup time reductions, massive setup time reductions by using our quick change system, but really, this applies to any quick change system. And the goal is to quickly and accurately change your fixturing. So change from one vise to the next, change from a custom subplate to a 3-jaw chuck, whatever it is. The goal is to quickly and accurately change your fixturing and tooling. The way we do it, we use a simple 4-pull stud system that's pretty common. We make ours backwards and forwards compatible with some of our competitors, which is interesting. We're from the job shop world, and we really wanted a system that's really kind of open source, kind of like what Autodesk is doing. We want to be able to help and share. So our system is actually compatible with a lot of our competitors, which we thought was really cool. We've purchased a lot of different systems in the past, and we didn't like that everyone had their own proprietary design that locked you in. So we tried to go with an open source. it's a standard 96 and 52 millimeter spacing, standard thread. So you've got, some universal system there, which is really, really great. But the goal of the system is, quickly change your fixturing, your tooling, and whether that's one machine or multiple machines, that's the name of the game. So one thing that a lot of people don't talk about, or we don't think about, is how does the quick change setup like really simplify the programming and the workflows. So that's one thing we've noticed a lot in our shop is whether it's just a one single machine. We've got some prototype guys that have one machine, all they run is that one machine, or it's other guys in our big production facility that are handling 30, 40 machines. The concept is basically the same. We have most of our programmers they also have to set up, so their time's kind of split, right? And I think that's true from a lot of people. So if we can cut down on our programming time and make them basically just more efficient, we can get more parts through the shop. So by using the quick change system, we've been able to really simplify and make the programming workflow more efficient, basically. And how we do that is basically we just establish work offsets. So we take our standard machine table and it basically saves master gauge locations. So in this example, we were going off a Haas, like a VF2, VF3, and we use a master indication palette to establish our work offsets. And so once we've got everything aligned and saved into our control, we have set safe position. So if we want to say change this small vise to put a Kurt vise on, or put this custom subplate on, our changeover time is seconds to minutes. Another big thing that we noticed is with some of our newer guys, our second shift, our third shift, a lot of new guys were more comfortable allowing them to set up the machines because it's nearly error proof. We've got set positions on the setup sheet. We say, hey, this vise, this position, next whatever job changeover, we want these vices with a picture or a screenshot of, how many vices, what positions, and we know they're going to locate within a couple tenths, and we've got nothing to worry about. So stuff that we would never do that in the past, allowing some of the newer guys to set up, more complicated setups. It's really simplified our whole workflow. So that's a major thing that really we've seen big efficiency gains. So here's a video. This is actually Tim Paul from Autodesk setting up his machine, which is actually in his garage, and he's making some motorcycle components. But he was able to set up our system pretty quickly, and he runs everything from master gauge locations. So you can see there, I mean, it's really simple. Tim's got a bunch of videos on his Instagram and Facebook of him changing parts and changing jobs, and it's pretty seamless. It's all, all the models are in Fusion. You've got everything you need. You save your positions, and you're off and running. So it's a really nice, clean setup. So the other big thing I wanted to talk about that we've, as a company, have really been focusing on, especially being in California and competing, all over the world, is really part density. So we really focus on maximizing our runtime. So whether it's, small run stuff, 10, 15 pieces, or it's, we've got a couple jobs right now, 30, 50,000 pieces, right? So pretty high volume stuff. So the concept we use is exactly the same, whether it's a prototype job or it's a big production run. We're trying to maximize our runtime And here's a little graphic that our good friend Mark Terryberry put together about just looking at the part change time and the tool change time. So the pie graph shows your standard one vise, breakdown of time and versus many vices. So you can see your tool change time is one thing you don't typically think about. Running 1-2 parts, how many tool changes you have. Plus, a lot of times there's, some sort of unnecessary moves that you're eliminating by doing multiple parts in a setup, and your part change over time. So that's opening the door, that's, literally pressing the start button and having an operator that has to basically babysit the machine, right? Because so our goal is in this particular setup is to run multiple parts. So our tool change time is considerably lower and our run time's longer. So that machine's just running and we can go program, we can run other machines, whatever we need. And all of that is made easier when we have models in Fusion. We're using products like, AirTurbine. We've got the correct tools from Harvey. Sort of all of that comes together to make the the whole workflow more efficient. So it's really everything. But our focus is been really maximizing the efficiency of every machine. So instead of adding more machines and putting 1 or 2 vices on a new machine, we're saying, all right, how efficient can we be with this one particular machine in terms of, setup reduction, running as many parts as possible. And then, once we've sort of got that dialed in, then we'll add a second machine and make that as efficient as possible. So I know a lot of people look at it and they go, wow, it's a lot. It looks like a very expensive, setup. And it can be expensive, but again, the ROI and all of these, whether it's our quick change system or somebody else's, you can, most of the time you can sort of like step your way into them, start with a couple, 1 or 2 plates, right? And see the efficiency from that. And then you kind of build it out. You don't need to, jump to, 2 parts to 32 parts. It's something you can ease into, but it's really amazing how much more efficient you can be when you start looking at multiple parts per cycle. So obviously vice rigidity is everything when we talk about, whether you're running 1 part or you're running multiple parts, everything has to be rigid. Your quick change base has to be rigid. The vice obviously has to be super rigid. But there's a couple things I wanted to talk about that we get asked pretty frequently in terms of this sort of newer style, small footprint work holding, right? We get asked a lot about the holding power and, it looks like you're not holding on to a lot of material. So there's some stuff that we do a little bit different compared to your traditional perk vise. So what we've done is, and a lot of our competitors have done similar stuff. We try and put as big of a lead screw in the vise as possible so that we get the max amount of clamping force out of that particular size. So for their small size, this particular vise on the screen is 5 inches by 6 inches, so 125 millimeters by 150 millimeters. And you get roughly about 5,000 foot-pounds of clamping force, which is, a considerable amount of clamping force at, mid 40 foot-pounds of torque. And in this case, we use a set of gripper teeth to bite aluminum and soft steel. So 55 HRC, 4140, other products are in that sort of similar range. We came up with a custom tooth pattern that actually bites into the material. So we'll typically over torque the material, make sure we get good indentation and then back it off and make sure that we get, good bite marks. But we only hold on to about 100 thou. We tested different depths, 200, 250, 100's a really, really nice number for just, you know, general roughing, but it gives us a lot of holding power in soft material. But a couple things we do. So there's ways that we have to, because the vices themselves are very small footprint. If you compare that, we make some bigger vices, 10-inch vices, and you know, your traditional Kurt vise that's substantially bigger. The sort of the length and the size of the vise body gives you a lot of rigidity. There's no denying that. So when we move to a smaller footprint vise, we're gaining access, we're gaining, you know, now we've got the ability to stack multiple vices. So there's a lot of advantages there, but there's some stuff we like to do that give us, you know, really good holding power and ensure that we don't get a lot of jaw lift. That's typically, you know, pretty common with a lot of the smaller vices. And it's not just jaw lift, the whole body of the vise actually flexes. We've done a lot of testing. It's the whole thing that moves because you've gone with a smaller footprint vice. You just kind of need to use them a little bit differently, kind of treat them more as a precision piece of equipment. But we did some in-house testing, and this is true for really, you know, any of the small vise stuff. Reversing the jaws, and we've actually got new versions of the vices that are coming out that have a 4-bolt pattern that actually give us pull down on the material. So that helps substantially. So you can see the jaw deflection is substantially less when we go to a reversed jaw configuration. So we do that a lot. We also came up with, and we have some, you know, competitors that have done similar stuff, anti-lift jaws. So what those do is they basically, it's a 2-piece cleat that has an angle and the jaw itself. So that puts the sort of the, you know, pivot point very high and forces the jaws down. So that helps substantially as well. So there's little stuff we have to do with these smaller vices to get them to do exactly what we want. But that's common stuff that people look at a lot and ask us about, you know, how do we properly use these things? So here's a little example on one of our 4th axis. So, and again, you'll see we're trying to be efficient across the board. So where in the past we may have run 1 part on our 4th axis. Now we're running, you know, 8 parts, 12 parts. So that the 4th axis is going to run continuously for, you know, an hour or so, and we can go do some other stuff. So across the board, we're trying to be as efficient as possible. And this is some mild steel that we're gripping on just with the gripper teeth to make this setup, the super easy. One graphic I did want to show, and this, you know, a lot of people ask about this. A lot of the smaller jaws, they offer a couple different clamping configurations. So we offer the standard jaw, comes with serrations that, you know, for softer materials. And then there's also a dovetail in there. So we're known for a lot of our dovetail products. You can utilize dovetail with any of our products, but you don't have to. So you can clamp them either way, or you can clamp them on the smooth face of the jaw. So this example shows the 45-degree dovetail utilized as about as rigid as you're going to get, especially if you're doing some super high-speed stuff, harder materials. We always recommend using the dovetail is a great way to go. But there was a couple of things I just wanted to point out that a lot of people ask us about is really proper dovetail. We use a 45-degree, but it's applicable to any dovetail you do, 45, 60, 10 degrees, 15 degrees. The material should sit on the top of the vice jaws, and we want clearance in the corners, and we want clearance at the bottom. And the reason we do that is the dovetail basically it's acting as a wedge. So it's really trying to split the material right in the corner. And what that's doing is it's sucking down the material and holding it in place. So we've actually come up with a couple general dovetail prep guides that you can use for any of the systems. And I can share those links with you guys. But the dovetail process is very simple, but preparation of any of the dovetails has to be done correctly, or you can have a slew of issues that are unintended from, you know, chatter to sort of the material bouncing. But if you know how to properly do that, it's a extremely rigid, extremely solid setup. And I'm sure if you guys follow us online, there's, you know, we hold material that's, you know, 3, 4, 5 times the size of our vise, which you would never be able to do by utilizing a small dovetail. Harder material, titanium, you know, heat treated stuff that's typically a nightmare to hold. We can use a dovetail. We're using those mechanical advantage to hold that material in place. And then we can go, you know, with high speed spindles, and we can use, you know, all the exotic cutting tool coatings and really see some major gains. And obviously, you know, better access to the material. So, you know, we can do stuff like this is buddy Phil up in Canada. I mean, he does components, you know, 3, 4 times the size of the vise that you just wouldn't be able to do without a dovetail. So there's some really neat advantages to it. As long as, you know, the prep's done properly and, you know, you kind of prove everything out, and your fusion, your cam pleat, there's some really, really great advantages to it. And again, so the last thing I wanted to talk about, which is something that Rob and the guys at Autodesk and I, we've all been working on, all of our full models are always available. So 2D, full 2D drawings, 3D models. We've actually got a new configurator that's coming online in about a week or so. That's going to be more machine specific, and it's going to be really, really cool. But we're working on a workflow to import directly into Fusion. So keep an eye out on that. But we're, again, just trying to do everything we can to make this process super efficient so that it's easy to go from, you know, okay, I need these couple vices, bring them into Fusion, start programming. You know, you have your vices out there on the floor. You tell those guys, you know, grab these 2, and just make the whole workflow as easy and simple as possible. Because, you know, we all have a lot of stuff going on, and if we can simplify some of this stuff, we're able to compete with, you know, anybody in the world. You know, no matter what the country, we can be efficient. And yeah, that's all I got, guys. So Rob and I will keep you posted with, you know, we're working on some pretty exciting new stuff with modeling standard products, but also machine specific products. So picking, making models, figuring out, you know, what's the correct diameter, what's the correct height. We've done a lot of that work, and we're kind of working together to make that all come together. That's all I got, guys.
Awesome, man. I can't wait till we make a better workflow there, because I think to me that's the missing component here when you do CAD CAM. It's like the painful thing about CAD CAM is importing or making tools or bringing in your fixtures. I mean, it's how do we improve this workflow? I mean, we have, like, I can order anything out of Amazon right now with touching my phone, but if I'm going to program something, I have to stop, go to a website, read all the details, fill that out in my software, regardless of what software you're at. You know, you need to fix that workflow.
Totally.
But yeah,
totally.
thanks. You actually have a couple fans there on the chat that were chiming in, so you have a couple of questions here.
Oh, thanks everybody.
You've got Matt actually in Pennsylvania from Micro Tools, and he actually has Harvey Tools, and he has 5th Axis Workholding. And he was saying that he saved cycle time by 30 minutes on.
Awesome.
I think he was commenting on something you said.
That's
and then there was
what I
another
like to hear.
question. If you want to answer, someone said, "Do I need to square my material before placing it in on gripper teeth vise?"
So that is one thing that you actually do not. So we've got a couple different products. Our standard self-centering vise, we actually built a little bit of float in the jaw, mainly for Op1 roughing. So you can just sock up material and pop it in there. That was the goal. We have some other fixed jaw versions that are a little bit more precision. If that float in the jaw is a problem, we have options for that. But the answer is no, you don't need to square it up. And most of the time, we prefer not to square it up because, you know, the jaws, they're actually going to bite sort of better. The way we designed that whole vise was for Op1 just roughing we just saw cut material, get it close enough. And that was kind of the way we designed that whole vise, was to not have to square it up.
Cool. That works for him, you said. And then I'll answer the question about tabbing in Fusion. So at the moment, there is not a dedicated tabbing operation. I mean, generally, because Fusion's CAD and CAM, right, you can design whatever tab you want. That's generally how customers have done it at this point. I know in other CAM systems, there are dedicated tool paths towards that. I know we're looking into it because I've seen it pop up here and there on a thread and the development team. So I'm sure if we do put it out there, you'll see it. You know, we like to announce like what capabilities we're adding. And as you know, Fusion's cloud, we're continually updating. Like in weeks, you know, I won't open this offer for a couple weeks and there's something brand new in there that I didn't know was in there. So look for that. If we do put it in there, I'm sure we'll announce it.
Yeah, I know that we're like John Saunders and our next like little video that we're doing is going to be about tabbing. So we'll probably have some, I think John's been working on some stuff inside of Fusion.
Awesome.
It's, you know, whatever he's got there, but that should be coming pretty shortly. We were working on that a couple of weeks ago before we all got, you know, everyone got sent to quarantine. But it's something that we get asked about a lot, and we get a ton of customers, you know, across the board, Autodesk,
right.
You know, of fifth axis users that have been, you know, having good success with tabbing. So we're going to do some, you know, teaching and a little bit of workflow. So I know John's working on that as well. So
okay.
Keep posted on that. I'm assuming he'll have some more slick tricks for that. And the last video I showed Phil Butterworth is a tabbing master. So I'm sure we'll involve him because he's like the king of tabs. He knows everything about him.
Yeah, for sure.
Hey, Rob, I'm not sure if it's just me, but it sounds like your mic might be has a glitch.
Yeah, it is getting a little weird.
Yeah.
Oh.
Sounded like Darth Vader or something.
Yeah, I was gonna say you sound exactly like Darth Vader.
Where are you coming from, Rob?
I'm in space right now.
Yeah.
I'll just stop talking. I'll let you take over then.
All right. I'll share my screen here.
Cool. All right, I think I gotta stop sharing.
Hey, thanks, Matt. It was incredible PowerPoint.
Absolutely. Let me stop sharing. Should be good.
Does everybody see that? All right. So let's get some energy going here, right? I know it's been a long day. There's been some good presentations. Matt did a great job. Tony, you started everything off. It was incredible. I'm going to kind of touch on a little bit of what Tony started. I just want to let everybody know that, so I'm used to doing these presentations. I've done them all over the country. I'm used to walking around. I'm a little bit animated. I like to get involved. So today I'm sitting at my desk, so no pants. Just letting everybody know, no pants today. I'm going to do this freestyle, all right? And give me a little bit more energy. So first,
just before you go on, I don't know if everyone else is seeing it, but there's a big black bar over the presentation. I think it's where you've got like the Zoom windows up. If you just minimize that.
How's that? Better?
Yeah, that's better.
Perfect. Thank you, Jack. Appreciate it. So I'll just introduce myself. First of all, my name's Don Grant. I'm the National Application Engineer for Harvey Performance Company, based out of Raleigh, Massachusetts. So I've been with the company for 4 years, background 32 years in the cutting tool industry. So I started way back in 1987. So I'm not sure if they let the wisest one go last or if they let the oldest one go last. So I'm going to say they let the wisest one go last. So we're proud to be part of this group. We're proud to do a presentation and hopefully educate some people with a little bit more micro machining. So let me just kick this off. but just kind of introducing ourselves a little bit. So we're Harvey Performance Company. So like I said, we're based out of Raleigh, Massachusetts, and the Harvey Performance Company covers 3 brands. The Harvey Tool brand, which is what we're going to talk about, which basically encompasses the miniature and specialty profile tooling. Harvey Performance also has helical solutions, and then Micro 100. So all 3 brands right here in the US, which is we're pretty proud of. All product is made right here in the US. We are 100% up and running, trying to support our customers, making sure we get tools to the proper manufacturing facilities to keep everything going here in this horrible time. So I am extremely optimistic. I just wanted to start off by saying that I think that you know, things are going to turn around real quick here, and we're going to get back to some really good manufacturing here in the US. So we're excited to educate in some of these downtimes, and we'll just kick right into it and get started. So let's talk about micromachining. Micromachining, as Tony mentioned, it's a different world. And with Harvey Tool, we have a lot of experience in micromachining. So when you're dealing with micro cutting tools, I call micro, see, this is where it gets a little bit different in different areas. I like to think of micro cutting tools as 3/32 and below. Some people go 1/8 and below, you can go 1/4 inch and below, and micro cutting tools can be 0.62 and below. They all kind of run differently as they get smaller. There's different rules that we need to apply with smaller diameter tools. I don't know why it says larger diameter. Oh, then with larger diameter tools. So let's explore some of the differences in the world of micro machining. First of all, I like this slide. This slide kind of shows you a little bit of a depiction of what we're looking at, what happens with the cutting edge as we're cutting material. If you look at the top slide here, you can see that this is a 1/2 inch tool, and don't get caught up on the 50 times magnification, but every cutting tool has a natural rounded edge on the cutting tool. So when we're taking a 1/2 inch tool and we're making a big enough chip, we're actually getting underneath the material with that cutting edge where we can actually plasticize the chip and get underneath it. When we take a smaller diameter cutting tool, let's say 30 thousandths, and we bring it up to 250 times, that natural rounded cutting edge that's on there, if we don't get a big enough chip or a large enough chip in there, you can actually cause the cutting edge to be negative versus positive. So I wanted to start off with this graph to kind of show you what's happening at the cutting edge. If we're trying to baby the chip a little bit too much or a little bit more prematurely than we would with a standard tool, we can actually plow and cause more deflection and more harm than good with a smaller cutting tool. I'm going to give you some more tips and tricks on how actually to apply that cutting tool, but I think this is a very good slide to kind of show you that that natural rounded cutting edge of that cutting tool can actually be negative versus positive if it's not used correctly. And that's where you get deflection, you get bad poor surface finish, and other issues that are going on. So let's talk about deflection. Deflection is a tool killer, especially when we're talking micro cutting tools. As the tool gets smaller and smaller, the forces against that tool get the tool to deflect. Actually, the force it takes to get the tool to deflect is a lot less. So as that tool gets a lot smaller, it doesn't take as much force to push that thing to get it to deflect. So we want to try and stabilize that cutter as much as possible. Think about this. If you double the diameter of the tool, it will result in 16 times less deflection. That's just doubling the diameter of that tool. If you double the length, will result in 8 times more deflection. So if we're actually going longer with the tool, we're going to get 8 times more deflection just by doubling it. So if we go from 15 thou to 30 thou on the length of cut, we're going to go 8 times. If we actually take the diameter, we're going to go 16 times less deflection by doubling it. So I thought that's a very interesting fact and something to think about when you can possibly go with a larger diameter tool. It really helps the deflection that's against the tool. So in that case, its core strength is key, right? When we're talking about miniature tools and we're talking about smaller tools, the core strength really has a lot to do with it. So versus using a 3-flute tool, you might want to start looking at tools that have actual more flutes for micro cutting tools. Now, Harvey Performance actually goes down to 0.2 millimeter with 4 flutes. So you can run under 8 thou diameter with 4 flutes. So as many flutes as you can put in there as possible is going to reduce that deflection by increasing the core strength on there. So if we can get the right core strength, go with larger number of flutes, which when you're thinking about micro tools, it's not something that you're kind of thinking of. When you think of smaller diameter tools, 15 thou, 20 thou diameter tools, you're thinking you're going to have less flutes. But it is possible to find tools that have more flutes in them, that has a stronger core, that's going to make your tool deflect a lot less. Okay, let's talk about some tooling tips. Number one, the biggest thing that we have to take a look at when we're talking about micro tools, I would say number one, before you even put that tool in the spindle, is you want to make sure your handling of that tool is correct. I can't tell you how many shops I've gone into where they just putting it in the holder, they'll break the tool. An 8 thou end mill, a 10 thou end mill, a 15 thou end mill. As that tool gets smaller, it's even more important to take care of that tool. You spend a lot of money on these tools. We want to make sure that we're not damaging them before we put them into the collet, before we put them into the holder. So it's important to make sure in the packaging, they stayed in the packaging until they go into the holder. You keep the plastic on the end of the tool before it's actually into the tool holder, and this will help prevent some of that damage that you're going to get on the tools before you even get started. Watch out for tool wear. Tool wear is critical, especially when you're running these tools. We need to keep them sharp. It's very important to get the tool, cutting tool. It doesn't matter if it's a 1/2 inch, a 1 inch diameter tool, or if it's a micro tool. It's important for the tools to be sharp. Sharp is key. So we wanted to monitor what our chip loads are. We wanted to monitor what our surface footage, whereas we'll get into a little bit more high-speed machining. We want to make sure that we keep that cutting edge sharp. It's a lot harder to monitor the cutting edge on a micro tool than it is on a larger tool. So that's why it's very important to get the right speeds and feeds, the optimal conditions of that tool before it actually starts cutting your material. Therefore, you don't have to worry about taking an 8-10 times loop and trying to see what kind of wear is on that cutting tool. It's going to be a lot harder. So what we're trying to do is to create a lot more predictability with these cutting tools when we actually run them in your applications. This is why it's important to select the right milling and drilling optimized material is key. So you want to make sure you get the right optimized cutting geometry on micro tools. You can obviously see which one's the good and bad before I actually put those up there. Green good, red bad, of course. I've done a lot of applications with a lot of cutting tools at the customer, and anybody that runs micro tools, there's an easy way to tell whether or not the tool is being successful, right? I call it IDB is the acronym. And that means after you run your application, you run your part. The main way to find out if you were successful is IDB, which means it didn't break, right? That's pretty much how we look at it. In most cases, when you're running a 10 thou end mill in a new application, we're looking to make sure it didn't break. So what we're trying to do is really optimize those geometries on those tools, give you the best performance. So when you put that tool in, you can hit the green cycle start button and know and have the confidence that that micro tool is going to perform. It's not going to break. You have the right conditions in your holder, your spindle, your workpiece, your right gripping. Matt did a real good explanation on your work holding. Tony did a great explanation on your high spin speeder heads, your RPM, and then of course, Jack talked about your program. All of these things are very important when you're talking about micro tools. So I think this whole thing really is a good presentation where they all add up to making sure that you can put your micro tools in your spindle and not worry about the performance you're going to get out of them. So as I said, picking the right geometry, okay? Here's a little plug on Harvey Tool. We have micro tools for material specific end mills. This is something we're pretty proud of. We have designed the cutting edges. We have designed the core strengths. We've designed the edge prep on micro tools, the corner radiuses, the reaches. All that information is in the Harvey catalog where you can look for your specific material, look at your micro tools down to, in material specific, like I said, down to 1/8 thou or 0.2 millimeter in diameter, and you can get the right micro end mill for that specific material. You can find it for hardened materials, exotic alloys, medium alloys, and free machining. So all these geometries have been designed with those right edge preps to handle the chip loads that we recommend in the right applications so they last, they perform, and you get the biggest bang for your buck. It's not about the cost of the end mill, right? It's about the cost of the cut. It's always about the cost of the cut. Same thing with drills. It's the cost of the hole, not the cost of the tool. It's very important to look at how that tool is performing and what is the cost of the cut. So that's why maybe looking at a material specific end mill might be a premium versus a standard general purpose micro tool, but you're definitely, the cost of the cut is going to be much better than using a general purpose. So all these material specific end mills that we offer for ferrous materials come with a variable helix. Now that's impressive. I've been in the cutting tool industry for 32 years. I started a company called Precision Twist Drill back in the 80s. And the fact that we can put a variable helix on a 0.2 millimeter end mill with 4 flutes that performs in your material is very impressive. Very impressive for somebody that's made cutting tools his whole life. Now, the reason we put variable helix on these small cutting tools is we're running an elevated speeds and feeds. We're running an elevated RPM, especially if you're running a high-speed spindle in these machines and getting up to 30, 40,000 RPM. You're getting a harmonic balance in there that the tool actually wants to start singing. It kind of wants to start vibrating on there. So what we do, and a lot of competitors also do, is they'll either put variable helix or variable pitch on end mills. A lot more common in your 1/4 inch, your 1/2 inch, your 3/4. But we do variable helix on our end mills down to 0.2 millimeter in diameter. So what this does as you're getting those elevated speeds is you're breaking up those harmonics. If you don't have variable helix, and you're not using a variable helix end mill, another nice trick to use is try and get an end mill with odd number of flutes. An odd number of flutes, look at your 3s, look at your 5s. Those will break it up a little bit if that tool is not variable helix or variable pitch. But if you can find something that's variable pitch or variable helix, you will definitely see a better finish. You'll see a better performance, and you'll obviously cut a lot freer with that tool. They help dampen the reverberations and otherwise lead to chatter. So very important to make sure you're using a variable helix for optimal performance. Tool coatings. Let's talk about tool coatings. Are they worth it on micro tools? Are tool coatings worth it on micro tools? I'm here to tell you absolutely, absolutely tool coatings are worth it on micro tools. Now there are some caveats to that, right? When you're getting down to 2 thou in diameter, 4 thou in diameter, 5 thou in diameter. Number one, you're not going to be putting tool coatings on some of the really small micro tools because the coating will actually round the cutting edge more than it will from natural carbide sharp grinding wheels. it will put a round corner on the cutting edge. So as you get smaller, you want as sharp as possible. So you have two things you're kind of fighting with the tool coating. You're fighting the roundness, so it's not going to cut as free. But then the caveat to that is if we're cutting free, the tool coating is going to add 30 to 200% of tool life. Okay, so the optimal way to actually get a tool with the proper tool coating is consult your experts, your cutting tool manufacturers, because what we'll do is we will optimize with our coating departments the thickness of those coatings for the micro tools. So we'll make sure that maybe we're not running a 4 micron on that or a 5 micron thick coating on that. We will run a smaller coating to make sure we get the sharpest cutting edge as possible on there. So now you can run with the coating, you can run with higher speeds and feeds. It acts as a barrier. It's key for micro machining, especially with the elevated RPMs and trying to get the surface foot. So it's not really elevating the surface foot with a micro tool. It's actually using the correct surface foot with a micro tool. It's not, it's kind of a certain way to look at it. So whereas you're running 200 surface foot, you're obviously going to be running on a 15 thou mil a lot higher on the RPM, in which case we're generating a lot more heat with that micro tool. Therefore, the coating is well worth it as long as we don't round the cutting edge too much so we start deflecting and pushing away from the material we're cutting. So it also adds surface lubricity. So we're also bringing in some lubricity, make it cut a lot freer, removes corrosiveness, irregularities on the tool. We're smoothing out that tool by putting that coating on there to let the coolant actually slide off the tool better, let the chip slide off the tool better. So by adding a coating to your micro tools, very beneficial. Now, if we're going to talk about coatings and micro tools and beneficial, we could get into 3 hours of discussing this whether what type of coating for what micro tool should we be using. And this is all conducive to what material are we cutting. Anytime you're talking end mills, anytime you're talking cutting tools, it really is a combination of the end mill, the drill, with the material that you're cutting. Every material has different characteristics. So it depends. If you were to ask me, should I use a coating on this end mill for my application? The first question I'm going to ask you is, what material are you cutting? What are you trying to do? What are your reaches? What are your lengths? And let's get you the right tool with the right coating, with the right geometry, so that you put that micro tool in there and you're going to be able to hit the cycle start button and walk away. So machine tool and operations. Use higher RPMs when possible. When you're talking micro tools, you want to use the elevated RPMs. You're going to get the biggest bang for your buck out of using smaller diameters to utilize the surface foot that is recommended for that tool to cut, okay, based on the diameter of the tool. As the tool gets smaller, it wants to spin at elevated RPMs in order to control the heat at the cutting edge. Tony talked about it a little bit. It's very important to get that cutting edge heat zone where the material meets the end mill at the right temperature, at the right speed to plasticize the material so that that end mill cuts freely and removes the material efficiently. So if we take a look at a 1/2 inch diameter tool, and we're talking about this and we're looking at 250 surface foot, that is going to tell you that we need to run that tool 1/2 inch at 1910 RPMs, which is usually well within most machine tools that everybody's running. If we just take a look at a 1/32 or a 31 thou diameter tool at 250 surface foot, look at where we're at in the RPM. The recommended manufacturer or us as a end mill vendor is going to tell you 250 surface foot is going to give you optimal performance in that material with that end mill. So now we need to run 30,806 RPM and some change. I'll take the 6 off of there and we'll say 30,800 RPM. I give plus or minus 1% on RPM to be successful, but you'll be fine. So what you're going to want to look at is you're going to want to start looking at these speeder heads. You're going to want to try and look at RPM increasers to get that surface foot to get optimal performance out of your end mill. Now there is a caveat to that, and I didn't want to. I do have some opinions that maybe we could break out in a chat group a little bit later on high-speed machining with end mills. There are some machine tool limitations. I just want to throw that out there. By far, best way to run a micro tool is by getting the RPM on your spindle to get the biggest performance out of that. But tool path is very important with that, because there are accel and decel rates on machines that can take a 2 millionths chip load. If you're not careful and you're running at elevated feeds, you can turn a 2 millionths chip load in a corner to 2 thou. And it will not be very good for your tool. So that's why I love this whole way we put this together, where you take the high-speed spindle, you couple it with fusion, adaptive clearing with the right tool paths, with the right end mills, get the combination of all three of those working together, take all the variables out of the machine tools, out of your spindle, out of your end mill, and you know what? Have one person running 3 machines instead of babysitting one all day. It's the right combination, but there are a lot of factors that have to go right in order to be successful with micro tools. I think we're doing about 5 minutes here. Does that sound about right? So let's talk tool runout here real quick. So tool runout, very, very important, as Tony mentioned, with micro tools as your tool gets smaller. Now, Harvey Tool actually makes a tool from 1 thou in diameter up to 120 thou in diameter in 1 thou increments. So we actually sell a 1 thou diameter end mill, uncoated. See, that's what I'm telling you. If we were to coat that thing, you'd probably have a hard time cutting with it. It's actually 2 flutes. It's 1 thou diameter. I always tell everybody it's plus or minus a thou on the diameter, guys. So if nothing shows up in the box, you got what you ordered. It's well within spec, so you're good to go. I'm just letting you know. So so it's very important to make sure when you're running those micro tools, 10 thou in diameter, 8 thou in diameter, 20 thou in diameter, you really want to make sure that you have the right holder, you have the right spindle, and your TIR or runout on that tool is very minimal. You will lower your tool life. You will decrease the part finish. You're not only losing the tool life and chancing breaking that tool, you're going to lower the finish that's actually on the outside of your part. Your tool life decreases 10% for every 1 thou TIR. The usual suspects are the spindle, making sure you have the right spindle. I think Tony was saying some of the runout on his spindles were around 2 micron, which is incredible. With the right collets, the right tool holder, make sure the machine was not crashed. That's always good. Less than 5 crashes a month is always preferred. Never crashed a machine myself. With my nose growing, of course, right? If you haven't crashed a machine, you never learned anything. So we all learn that way. Short tool shank grip. This is very important too. And another shout out to Harvey Tool, because we're involved in this presentation. Make sure you get the right reach with the right shank, okay? A lot of people are trying to get past holders, fixtures. Another plug out to Matt here over at 5th Axis, getting the right fixture, the work holding, making sure that you got the right amount of shank up into the holder for you're getting max rigidity, okay? Very important, right holders. So make sure you're looking for that right tool that has the right length, reduced neck to give you max run out coming out of your spindle. We talked about part finish. Okay, tool run out is equal to pour surface finish. As your run out gets larger, Tony touched on it earlier, you will not cut on every flute evenly. If you're running out 1/10, okay, and you're taking a 2 millionths or maybe a 5 millionths chip load, depending if you're running a 10 thou tool, your teeth are going to cut inconsistently. It's going to cause bad tool performance. You're not going to get tool life out of it, and you're going to get that irregular shape as you see on the bottom there. So your actually RA finish will not be as nice as it would be if you were running good TIR on there. So how do you check TIR on a micro end mill, 10 thou end mill? I can tell you this right now, don't put an indicator on it. Please don't put an indicator on it. It will not go well, especially a one thou indicator probably won't work well. This is what I tell everybody to make sure you're getting maximum TIR is really check your boxes. Make sure you have the right holder. Make sure you have a brand new collet. Make sure it's cleaned. Make sure everything's running out. Most micro tools come on a oversized shank, or I should say all micro tools come on an oversized shank. You can check the run out on the shank to make sure your collet is running out correctly, and then I would say assume, guarantee with Harvey Tool that we ground it correctly and the TIR is in within tenths, if not millions. So I like this slide here, and this is very important to a lot of people that are actually slotting. Are we slotting with a micro tool, or are we making a slot? I'm here to tell you, you're making a slot with a micro tool, you're not slotting. Anybody that runs standard end mills in any kind of slotting situation knows that traditional slotting is all about chip evacuation and flute count, okay? So what you're trying to do in traditional slotting with a 1/2 inch end mill is use the fewest flutes possible to get the chips out. That's what we're trying to do. When you come to micro slotting, it's all about rigidity, deflection, and core strength. Trust me when I tell you guys this. I have been at the spindle over and over. Medical companies put as many flutes as possible in full slotting with a micro tool. Do not worry about chip evacuation. And let me explain this real quick, okay? When you're running a 10 thou end mill in a full slotting application, you are not running anymore, usually. Now you can tell me different, usually 2 or 3 thou axial depth of cut running at maybe an accelerated speed and feed. When you run a 2 to 3 thou axial depth of cut, chip evacuation is not your problem. Your problem is when you get down to the bottom of that, you're putting force on the tool. That's what's wearing it out. That's where I'm telling you, put as many flutes as possible in that micro tool as you can. Harvey Tool runs 5 flutes down to 15 thou in diameter. You will be successful. I have gone from getting 2 parts with a long reach tool by adding as many flutes as possible in there, 5 flutes, from going from 2 parts to 15, 20 parts with the same diameter tool. It's very important. Another thing you might want to do is if you're doing a slot, you can add the strongest corner as possible. In some cases, even a ball nose. You can slot with a ball nose all the way down to the bottom and clean up your corners with a square corner. Slotting with a ball nose is not unacceptable and can yield you better tool life than if you're having a big issue with other square corner or corner radius tools. So don't leave out slotting with a ball nose tool. So there's many decisions to make, and I see we're winding down here, so I'm going to close with a couple things. So you have many decisions to get your output, right? A lot of things go input before you can actually figure out what your output is. So you're inputting stuff like the machine tool capabilities, tool holding, the rigidity, work holding, tool path. What is my tool path? Am I roughing? Am I finishing? Part geometry, how am I holding it? All this stuff goes in before you can actually start outputting these certain things on the right. Now I can figure out this is how my part's running. Now I can run these speeds, run these feeds, radial depth of cut, axial depth of cut, and these are the coatings I want to put on there. It's very important to make sure you go through all these inputs of everything you're using before you can figure out exactly how you want to run that tool. And when you're running a micro tool, how many shots do you get on this? I mean, we would all love to buy one 10 thou end mill and say that's going to get me through the whole job. That's the ideal. That's the goal. We know that's not reality in most cases, but that's the goal, and that's what we want to do is actually just get one end mill, get through our part, and then move on from there. So see the forest through the trees, guys and gals. I'm sure we have some both joining us, which is great. But see the forest through the trees. Know your application material, work holding, machine conditions, tool holder condition, tool choices. Know your surroundings, causes, effects, everything that's going to affect that tool to deflect, the reaches, the lengths, how it should be cutting, chip loads, speeds and feed, the situation at hand. And don't be afraid of change. Embrace it. Something might work for you. Try different things. Consult your cutting tool manufacturer, consult your work holding, consult your tool path professionals, spindles, consult those guys. So I love this saying, don't waste time learning the tricks of the trade. Instead, learn the trade. James Charlton, very good saying. I appreciate everybody's time. Thank you. And I think we'll have room for questions after this.
All right, I'm checking in. Is my mic all messed up still?
Yeah, you're
good
sounding
now.
good.
Okay. One question, Don, that came up. Touch-off techniques with micro tools.
Yeah, so this is a good question. So I was testing some drills, and we actually touched off on a drill down to 10 thou in diameter, and it was scary. So I'm telling you, the best way to check your micro tools is non-destructive or offline would be the best way to measure. If you're talking about taking a 10 thou end mill and touching off on a probe, probably wouldn't suggest it. Is Rob talking?
Can you hear me now?
Oh, yeah, we got you. We
Okay.
got you, man. Sorry about
No,
that.
no, that's me. I was Zoom 101. I was muted myself. Okay, so I was trying to tell you guys if I unmuted all the mic, or I allow you the ability to unmute your own mic. So if you do want to just chime in and ask a question to any of the guys that presented today, feel free to unmute yourself. The question came up. Yes, I'm recording the session, so we will post this, and we'll make sure to email everyone to find out where it's actually going to be posted. We're just still trying to figure out the logistics there, but yeah, it's open for questions now if you guys want to ask anything.
Hey, quick shout out to Les Thornberry that I see there.
Hey.
How you doing, Les, man? It's
How you
good,
doing,
good to
Don?
connect with you guys. How you doing?
Absolutely. Hey, stop talking about how old we are.
Yeah, I know, man. We're getting old, Les. We're getting old. That means we're
started-
getting wiser.
There you go.
That's right. We'll take it.
No doubt.
Good to
Thanks.
see you again, Les.
You too, Don.
Don, I missed this presentation that you had. Did you come up with this presentation on earlier stops for the tour?
This
Yeah.
one that we
Yeah.
actually did?
Yeah.
Yeah. There was it kind of mutated a little bit, Rob.
Okay. Yep.
But yeah, we've added some content. We've and listen, for a half an hour, just to let everybody know, you can only get into so much detail. There's a lot more that goes into micro tools. I'm sure Tony and even Jack, as far as the programming goes, and Matt, this is, you can dive into this for a week session, really, and just to understand everything that's going on at the spindle. That's why we offer our services, me as a national guy, us as a company, Tony and the rest of them, for actually one-on-one at the spindle to solve problems. So if there's ever anything like that, please give Harvey Tool a call, give anybody else a call. If it's the right situation, we will send somebody in there. We have qualified application engineers all over the country, have similar experiences. We will be there at the spindle. We will press the cycle start button. We will run the tools with you and make sure all those things line up.
Bold statement, Don. That's really awesome.
Yeah. I don't know if I'll be traveling anytime soon, but we'll see.
Yeah.
Yeah.
And shout out to everybody that's doing anything that supports the rescue effort for all the COVID-19. Anybody that's involved in ventilators, masks, anything, big shout out to all you guys.
That's a really great point, Don. I should mention that too. As far as Autodesk is concerned, we're actually assembling a response team to everybody that who's assisting with that. If we can help out in any way by providing engineering services or software, you name it, we'd love to get involved. So please feel free to reach out. Again, when we follow up an email, I'll put my contact information in there. So if there's anything we can do from a software standpoint, please let us know.
I had a customer call me this morning, short story. They were having issues with, they're making ventilators. They got to deliver 170 ventilators by next week. And they're having chatter with the chamfer cutter. So we're trying to dissect it over the phone. I told them they're in Michigan. You let me know. I will jump in a car. I will come out there. We will fix the problem at the spindle if you need to, if we can't get it fixed over the phone. More than happy to do stuff like that.
That's awesome, Don.
Yep.
There is a detailed question on the chat that you might want to take a look at.
Well, let's take a look.
Yeah, I'll let you read through. While you're reading that, Don, I do want to reiterate that, yeah, having a 30-minute platform isn't enough to really dive deep into some of these topics, but it's a great opportunity just to kind of showcase what's out there and just continue to educate the community. If you guys are interested in doing something more along these lines, as far as webinars like this, where it's stretched out a couple hours, where we're all at home and we can virtually connect with each other, and maybe we'll break out into smaller groups and do things like this. Again, please provide us with that feedback. We're happy to start ramping up some of more of these seminars. Maybe we'll do more workshops, actually walking through a process of, whether it's tooling or work holding or spindles or programming, etc. So a couple more in there, Don.
Yeah, this is great. So first of all, you want me to answer them here? Or you want me to just type?
Yeah, I guess I'm sure I'm still recording too, so I'm sure because the chat will be shared out as well. So I'm sure people might have the same question. So it's not a bad idea.
Yeah, so when you're ramping with micro tools and you're adding a lot of flutes, he's using 6 and 7 flutes and ramping and having issues. The big key with micro tools with anything when you're adding flutes is it reduce your ramp angle. I know I hate that, but what I would side with more flutes, because nobody wants to reduce the ramp angle depending on how deep the hole is, because it reduces cycle time. You are better off reducing the ramp angle and running a higher feed with the tool. So bring the ramp angle down to maybe 0.25 or 0.5 on the ramp angle on a micro tool 060 tool, increase the feed. And I'm going to give a plug out to Fusion 360 on here. Make sure you put a ramp taper, that Fusion 360 2 to 3 degree taper in there will help get the chips out a lot better on more flutes. So if you can add a taper, depending on what cam package you're using, that will definitely help evacuate the chips on micro tools. Micro drilling. Recommended drill suppliers for 0.35. So you want me to recommend drill suppliers, right? 0.35. Hey, Jeff, how small do we go on micro drills? But that's 2.25 millimeter deep. Listen, we're all in this game together. There's a lot of great competitors out there. And I think I saw some Kyocera guys actually on this call. A big shout out to Kyocera. We're accepting applications. If you want to come over to Harvey, it's all good. So, but Kyocera, I mean, there's a lot of good brands out there. There really is a lot of good brands. If you're looking at some of the best drills that we don't offer at Harvey, Mitsubishi makes a really good drill. Goering makes a really good micro drill. They're really good suppliers for that. But when you're micro drilling, it's the same principles apply to using a micro end mill, right? It's feeds, chip load, chip evacuation, cooling through how deep the hole is versus diameter, packing, non-packing. And then again, having a high-speed spindle or having coolant through that spindle too as well is very critical. There's a lot of factors that kind of line up. Yeah, he just said, thank you. That might be a good issue. I reduced my feed. A lot of people reduce the feed. And I'm here to tell you that, especially in titanium, I'm going to tell you right now, I can increase tool life usually in micro machining with an ML in titanium by 10 times, 5 to 10 times by taking a bigger chip with micro tools. Be very careful. Titanium likes to push. It's going to push your M mill away. It's going to deflect and stuff like that. Get underneath the material with the micro tool. Take a big enough chip. We can give you recommendations. You will see an increase in tool life.
All right. A couple
This
more
is
minutes.
great. Let's
Yeah,
just
we'll leave it.
all day.
Leave it. Yeah, rapid fire it. I mean, you're not going to get this panel of experts often on a call like this. So please feel free to shoot your questions our way.
And just for the record, I am wearing pants.
You don't have to lie.
I just
Hey, Don,
I took mine off when you said. I thought that was a new thing.
Nice.
Don, just to follow up on what you were saying about how some materials love to be pushed when you get into those smaller diameters, and titanium was one that we learned about as well when we were going 50,000 RPM, and we didn't even use a PEC, and it blew their minds.
Yeah.
You know, you just go straight through it. And I believe that was a 12 thou diameter tool at that time. When I was in Korea, and that video I was showing just a little while ago with that 2 thou diameter drill and in that hard steel, I'm not going to give the exact details of what we did because I feel like that would be unfair to the privacy of the company I was working with. But if we can translate quickly into millimeters from inches, the original feed rate was at 10 millimeters per minute, and the original PEC depth was at 0.02. By the end of this successful test, we were at 100 millimeters per minute at a PEC depth of 0.04. So we were able to multiply the feed rate by 10 times and double the depth of that PEC in that hard steel as we got smaller with a higher RPM to generate that success, which also gave longer tool life to that 2,000th diameter drill. So you're exactly right, Don. Just a little bit of putting an actual program and video we were looking at with the results and the programming of the test.
Right, Tony. And every material creates a different chip and it breaks differently, right? So it's very important to understand how that chip's going to break. And sometimes more feed, more cut, more heat, depending on what you're doing, which kind of goes in with what you're doing with elevating the surface footage on smaller tools, that will break the chip differently. So sometimes there's a sweet spot in there, but it's important to break the chip in the right material so you're not having the chip be an issue with what you're machining.
Exactly right, yeah. And again, and all of you guys touched on this, this I think is the reason why we all came together to offer this support industry-wide for everyone, because you know, Jack and Matt and Don and myself, we all touched on a little bit of each other, but more in depth to our specific, where our true talents are. And there are pieces I learned today from each one of you that I didn't know from the other presentations. And even for me, this was extremely beneficial. And I plan to watch this, you know, a couple more times going into the future, because I know that when I'm going to go do some air spindle work, that they'll ask me programming questions that you answered, Don, and they'll ask me rigidity questions and how many vices can I put into a machine that, you know, you went over, Matt, and also with the programming, Jack. I don't know how many times I'm asked, as we were just having questions on here about the drilling and what about my ramps in and ramps out and programming. This has been extremely beneficial for me, and I'm grateful that all of our companies have come together to offer this type of platform instead of individually offering our unique techniques. I think it's a wonderful thing. We got MJ in the background for Rob now, so I think he's
Khalil, man.
Yeah, I know. That was a win too.
Really good stuff, guys. Really good stuff.
Yeah, it takes. I mean, we've all been in our respective industries, right, for a while, but it's a constant learning. That's the thing about this industry. You learn all the time. I mean, Don, you called it out about the taper inside of Fusion. When I came on board to Autodesk and started learning Fusion, I questioned why they did that. Then I actually did a couple cuts with them, like, oh, I 100% understand why that's there. You know, it's
crazy how much better it is, and the crunching goes away right away when you add 2 degrees taper in there.
Yeah, there's things that I've learned across the way with working with Matt and work, you know, fifth axis and dovetailing, the proper way to do it. Yeah, you just like been in it over a decade, but you constantly learn. There's always something new to learn. So it's great when we all get together, because it's hard to learn all that in one, you know, if you're in just one shop and not being exposed to everything else, this is the perfect platform to be able to see a little bit of everything and kind of get your mind open to what else is out there as far as technology.
And I hate to say it, if you never crash a spindle, if you never break an end mill, you never break a drill, you never learn anything, man.
Yeah. You just hope it's not terrible.
I learned a lot. I have learned a lot. Crashed enough spindles, broken up drills.
Yeah. One of the when I first got brought on to AirTurbine almost a decade ago, that was kind of my job, was to break everything. I think I must have broken spindles and drills and end mills daily. So yeah, best way to learn. Wasn't always awesome at some other companies, but definitely the best way to learn.
That's right. Well, I had my own business for 10 years, so when you break an end mill, it comes right out of your pocket.